Hello, everybody. Welcome to this IEEE virtual reality paper session on augmented reality. My name is Dieter Schmalstieg and I will be chairing. I think it is very exciting that we are starting off with augmented reality as a topic. And in order to make us the most of our time, we'll get right started. Our first paper is entitled 3D Curve Creation on and Around Physical Objects with Mobile AR. This is a journal paper and it will be presented by Hui Ye of the City University of Hong Kong, China. And this is joint work with Qin Jung Quan of University of Constance, Germany, Hong Bo Fu, also University of Hong Kong. So thank you.
Okay, thanks for introducing. Hello, everyone. I'm Hui Ye from City University of Hong Kong. I'm happy to present our work 3D curve creation on and around physical objects with mobile AR. 3D curve creation is a fundamental operation in many graphics applications. Creating curves in situ makes the curves closely interacting with the physical environments, enable many applications such as 3D sketching, animation, and measurement. The recent advance in motion tracking allows to use a mobile phone to draw 3D curves in situ, making 3D content creation more accessible by everyday users. But most existing works are relative drawing, that is, drawing 3D curves from 2D screen. It is not intuitive to create 3D curves with complex shape. We want to explore absolute drawing, that is, drawing the 3D curves using the mobile phone movement. However, a mobile phone is different from a pen, so it does not have a predefined input point as the pen tip, and how to naturally hold the phone also remains as a question. Meanwhile, moving the device on and around physical objects may lead to the lost tracking due to the camera occlusion. It leads to curves with tracking errors. So we conduct two studies to figure out these two problems. We first conduct a user study on input point. Each participant was asked to use a mobile phone as a 3D pen to trace along the red tapes in 10 scenarios. And we asked them to define the input point of the phone and hold the phone naturally to create 3D curves. We categorized the observed input point into 7 types, and here are the corresponding preference percentage. The top 3 preferred input points are top left corner, bottom left corner, and back camera. We also divided the types of phone grasp into 6 categories. We also found that the participants usually pair the choices of input point and grasp. We suggest the top 3 preferred pairs for natural interaction. Second, we ran a quantitative experiment on the tracking errors of ARKit, and we created 3D curves with mobile phone using ARKit in similar scenarios to study 1. A mocap system is used to gather ground truth data. Then we manually categorized the tracking errors into global errors and local errors. Please refer to our paper for more details. For error frequency, pair 1 had the fewest error times. So we suggest use pair 1 for natural interaction with the lowest initial tracking errors and the natural interaction. However, although this pair has the lowest tracking error, it cannot be ignored as you see in this figure. So we present a system supporting both in-situ curve construction and interactive curve refinement to reduce tracking errors. The curve creation consists of 3 phases. In the authoring phase, the user moves the phone like a 3D pen to create 3D curves. And we can see the original result contains a lot of errors. So our system first provides an initial correction, removing part of the errors. For our other errors, our system provides users with 3 techniques to interactively correct them. The created curve is defined in a word coordinate system. To move the curve globally, we provide 2 techniques to relocalize the word anchor. First, the user can tap on the plane to localize the word anchor. Then the user can use the two-ray intersection to localize the word anchor. And users can also specify the target point that a curve must go through. The user taps a point on the curve and also uses ray plane intersection or two-ray intersection to determine the corresponding target location. For 2D sketching, users drags a curve segment and freeze the camera view, draw a desired 2D curve. Then the curve will be moved to the corresponding shape. So with these interactions, a desired 3D curves closely interacting with the physical objects is created. Finally, we conduct a global optimization, and our objective function consists of 3 terms. And please refer to our paper for more details. To evaluate our system, we recruit university students to perform in-situ freeform curve creation. And next, I will show you some results. This result contains several curves around the human body, and they are not easy to create by existing method. Sorry. We can see the curves created by our system is better than the original one. And our system also helps users refine a lot of undesired curves, making the whole results more constructive. Our system also supports to measure the curves on and around physical objects accurately. To conclude, the main contribution of our work are first is the illustration study on input point and the quantitative experiment on tracking errors, and a proposed system supporting in-situ curve construction and interactive refinement using mobile AR. If you have any questions, welcome to contact us. Thank you.
So the next speaker is Julia.
Thanks. Sorry. Hello, everyone. Thanks for the introduction. And welcome to the presentation of our paper, Augmented Reality Maritime Navigation Assistance, Egocentric Depth Perception in Large Distance Outdoor Environments. My name is Julia Hertel, and I'm from the Human-Computer Interaction Group at the University of Hamburg in Germany. Augmented reality presents a promising way to improve nowadays maritime navigation assistance by blending virtual content directly into the user's field of view. For such interfaces, it is crucial to ensure that users can correctly interpret the location of displayed virtual objects. So in our work, we wanted to know how accurate persons perceive large egocentric distances in outdoor environments using optical see-through, augmented reality, head-mounted displays. Furthermore, we investigated how different design attributes influence depth perception. There are multiple ways to assess depth perception, like verbal reports and blind walking, which can be used in real, virtual, and augmented environments. We used a protocol that is unique to augmented reality scenarios, perception matching. This protocol allows us to investigate the depth perception of virtual objects directly compared to real ones. In this work, we interpret the results of the perception matching task as follows. The participant is asked to place a virtual object at the same distance as a given target object. Thus, when the participant confirms, they perceive the distance of the virtual object to be equal to the distance of the target object. If, for example, the participant places the virtual object in front of the target object, the virtual object's distance is smaller than the target distance object distance, but perceived as equal and thus overestimated. However, it is important to note that in previous perception matching task experiments, the terms underestimation and overestimations were often used the other way around. Current literature mainly focuses on depth perception in indoor environments and short distances. Here, in perception matching task experiments, the judged distances are usually smaller than the target distances, which we consider as an overestimation. In blind walking and verbal reports, usually underestimations are found. The visitor space and outdoor settings are barely researched yet, but there are first indications for a bias shift for both larger distances and outdoor settings. We performed a perception matching task in an outdoor environment with 5 distances up to 75 meters. We included 3 visual attributes as independent variables, 3 different colorations, red, blue, and red-blue triggered, 2 shapes, a cube and a torus, and 3 different relations to the floor, placed on ground, placed off ground without a shadow, and placed off ground with a shadow. To avoid learning effects, we randomized the initial depth and the size of the object for each trial. So overall, we performed a full factorial experiment with 270 trials per participant. We invited 15 participants with a mean age of around 27 years. We performed the experiment on an empty parking lot, where we placed one more target object. The participants were standing at a fixed area, wearing a HoloLens 2, noise-canceling headphones, and an Xbox controller. For each trial, they were asked to move the virtual object to a specific target object. They could translate the virtual object along a forward-facing axis to align it with the target object. Based on the current scientific literature, we formulated 5 hypotheses. Firstly, based on the perception matching task experiments in short distances, virtual objects are perceived farther away and thus placed closer in action space. In vista space, we expect a bias shift. Secondly, the matching task error will increase with an increasing target distance. Additionally, we formulated hypotheses about the visual attributes we investigated. For coloration, we expect blue objects to be perceived farther away than red ones. Furthermore, a checkerboard texture will increase the matching task accuracy compared to a uniform coloration. Regarding the shape, we expect an increased accuracy for cubes compared to tori. We expected that, in general, an object placed off-ground, hovering above the floor, will decrease the perception matching accuracy compared to an object placed on the ground. For object placed off-ground, the drop shadow runner below the object will increase the accuracy. At first, we took a look at the first hypothesis, which predicted an overestimation up to 30 meters and an underestimation beyond. The results only supported this hypothesis partially. We found an overestimation across all distances, with an average error of 14%. Furthermore, we expected an increased matching error with an increasing target distance. However, this could only be found for the action space. We successfully fitted an asymptotic function, which suggests a maximum error of minus 9.5 meters. We found a significant main effect for the coloration on the assigned matching task error. As expected, blue objects were perceived farther away. However, no distinct difference between the texture and the uniform coloration was found. As expected, we found a larger accuracy for cubes than for tori. Regarding the relation to floor, we found significant differences between all of the 3 levels. As expected, adding a shadow increased the matching task accuracy for objects placed off-ground. Surprisingly, for these objects, the accuracy was even higher than for objects placed directly on the floor. All in all, we found an overestimation across all distances. The virtual objects were perceived in front of the target objects. Following our interpretation, these results coincide with similar experiments, but contradict the results of verbal reports and blind walking experiments. The higher negative errors for blue objects suggest that blue objects are perceived even farther away than red ones. We think that the main reason is the lower brightness. Regarding the shape, we found a significant difference but subjective feedback indicates reasons beside the dimensionality itself. Regarding the relation to floor, the results suggest that there's a visual relation, like a drop shadow, increases the depth estimation accuracy strongly. To gain first insights about how the results we found could be transferred to a maritime environment, we conducted a pilot study in a port setting. We invited a member of the local port authority for a think aloud session on a ship. Using the HoloLens 2 and an Xbox controller, the participant could freely move around various virtual objects and alter their design attributes via button press. The pilot study supported our main findings. Brighter objects had a better visibility, which seemed to facilitate the depth perception and visual relations to the floor, improve the depth perception as well. So in this work, we found valuable insights about the egocentric depth perception in AR outdoor environments in distances up to 75 meters. However, limitations and open questions remain. We propose the need for further research to investigate the depth perception in similar environments by using different assessment protocols and explore even larger distances, more sophisticated renderings, and maritime-specific characteristics. Thanks for your attention.
Okay, is my audio good? Okay. So hello everyone, I'm Leonardo Pavanato from Virginia Tech, and today we'll talk a bit about our work on evaluating augmented reality virtual monitors for productivity work. This work is a partnership between Virginia Tech and Microsoft Research. So while the value of multiple large physical monitors is well established for productivity work, the context of an increasingly work from home world introduces some impediments to productivity, such as the limited number of monitors, the need for physical space to set the devices, and the lack of portability. So therefore, our objective was to investigate the effects of replacing or extending physical monitors with virtual ones for productivity tasks. The concept behind virtual monitors is to use AR glasses to display floating monitors around the user, which would allow them to take their office anywhere, from their home to a moving train. This idea has been envisioned for a long time, from academic papers to science fiction movies. But now we have reached a level of technological advances that give us the opportunity to explore what that means for productivity work in terms of benefits, limitations, and new capabilities. Potential benefits such as not occupying physical space, being portable, and having any number of monitors, and potential limitations such as lower readability and a smaller field of view. To investigate, we developed a prototype that displays Windows 10 through a HoloLens 2. The three conditions we explored were physical, which had 3 physical displays side by side, hybrid, that combined a central physical monitor with 2 virtual monitors on the sides, and virtual, which contained 3 virtual monitors. It's important to note that the virtual monitors had 1.5 times the angular size of the central physical one, so from the user perspective, and they were positioned at 2 meters depth. This was done to achieve a similar readability level and also to reduce the accommodation vergence conflict. So we investigated 2 research questions. Our first one was to understand the limitations of virtual monitors when compared to physical ones, considering the current state of the art. And a second question was about the benefits of a hybrid physical virtual setup compared to a purely virtual one. We conducted a user study where 18 participants worked on documents to answer a report. We conducted in-person individual sessions of 90 minutes and investigated our 3 conditions: physical, hybrid, and virtual, within subjects. For each consecutive trial, we used a slightly different data set to reduce learning effects. The condition order was counterbalanced using Latin square. And then we measured performance, accuracy, head and eye tracking. We also had ratings on statements, ranking questionnaires, and in the end, we did a semi-structured interview. In the task, the participant acted as a head teaching assistant of a class, And they had to use all these windows, which were already positioned across their monitors, to answer a feedback form. So our results show that both virtual and hybrid are feasible approaches for conducting productivity work. Participants completed all conditions and achieved similar accuracy scores. And this was reinforced by the individual ratings, where we found no statistical significance on I think I was able to focus on my work, and I felt that I delivered a quality result on the task. So our first takeaway is that virtual monitors can be used now for real-world work, at least for short periods of time, using current technology. Going deeper, virtual is still less usable than physical, however. Overall, task time was 14% longer in virtual, which could be tied to a longer time to switch between the monitors, as we also had 50% larger head rotation amplitude and 23% more accumulated head rotation. Users also had 20% less visual attention switches, which could be related to the smaller peripheral vision. Also, users were less confident in virtual, with first order in ranking. Individual ratings also show that they had less trust to do serious work and more difficulty glancing at content. So our second takeaway is that there is a need for higher resolution and field of view devices, which could enable the use of smaller monitors that would require less head rotation. And as we can see in the graphs for task time and user ranking, hybrid acted as a middle ground between physical and virtual. We found that hybrid approximates virtual when there is more interaction on the side monitors, such as keyboard use, and it approximates physical when the task is more restricted to glancing at the side monitors while using the central monitor. Which leads to our final takeaway, that under current technological limitations, it seems to be better to extend physical monitors than to switch to completely virtual ones. That happens despite the existence of mismatches between the displays. And one of the reasons is that a physical monitor next to a virtual one may reduce the effects of lower field of view, as the peripheral vision can still be used. So we got some good results so far, but there are still so many directions we want to take in the future, such as how do these results change with higher resolution or higher field of view devices? What are the benefits of extending a single physical monitor with virtual monitors? What issues occur during long-term use of virtual monitors? And here we are especially interested in fatigue. And how can we take advantage of the flexible capabilities of virtual monitors, such as position, size, shape, and visibility? Thank you for your attention, and please ask any questions on Discord.
Yeah. Hello, everyone. I'm Miraj, part of PNG. Today, I'm presenting DreamStore, a data platform for enabling shared augmented reality. This project was done during my dissertation work at The Ohio State University, advised by Professor Arnab Nandi. So why do we need a dedicated data platform solution for shared AR? If you look at the top picture on the right, it shows a number of queries generated by an AR client every 100 milliseconds on one of our prototype apps. This number ranges from 0 to 13 every 100 milliseconds. If the system would have to serve 130 queries per second, and that's from a single client. Imagine sustaining this query workload for hundreds or thousands of clients. Moreover, if our data system does not have a way to prioritize incoming queries and the UI visualized all the generated results, we would have this extremely cluttered view for the users in spaces that are rich with AR objects. With these challenges of AR interfaces also come opportunities for improving system performance. Since human visual attention is selective and it's limited, the interface generated queries do not exactly portray the set of objects the user might be interested in. Another interesting aspect of the workload is that the access pattern of the objects is bound by the spatial placement of the objects in the real world. And this can be exploited into formulating a prefetching and caching strategy. So here are our main contributions in this paper. DreamStore is a principal data framework for building AR applications. It allows AR app developers to build apps as simple data management workflows, and they don't have to bother about the details of data synchronization in a shared setting. We provide ways to reduce and prioritize the interface-generated queries to reduce visual clutter and improve system performance. We also employ prefetching and caching strategy that employ the physical placement of the AR objects. We use the UI-generated query distribution as a proxy for user focus. The assumption being if the user is interested in certain objects, they will focus their capturing device on it. The objects queried fewer times than a set threshold are dropped from the list of backend data queries. We then further prioritize this reduced queries by frequency and fetch the AR object information from the backend at varying levels of detail according to their priority. We use the user's current location and their movement pattern to predict the next likely set of objects to be queried, and they are prefetched from the backend into the local client cache. So this is DreamStore's system architecture. The backend data store is a key value store that houses the information on all the AR objects. It's keyed on their identifier, a unique identifier. The user interactions through implicit and explicit gestures trigger object detection and tracking module, which identifies spots in the view for which there is information available in the remote store. The user gestures combined with the object identification information are processed by the interaction mapper that maps a seemingly large number of data queries to a well-defined reduced set of DreamStore database interface calls to the client-side cache, which is called AR view. Additionally, the interaction mapper module uses the client device's current position, orientation, and direction of motion to generate the set of object identifiers to be prefetched from the remote store. AR view is maintained using a proximity-based cache replacement policy. When the cache is at capacity, the object farthest from the recently queried set of objects is removed. So we evaluated our system on two different workloads. IPS is a synthetic workload. It was generated from the training data gathered for user movement prediction on an Indo positioning system. The generic workload was obtained by profiling a room scanning app with multiple AR objects in a small space. And for each workload, we have 1,000 simulated user sessions. For more details about the workloads, please refer to the paper. And we tested these workloads on 3 different system configurations. The knife setup implies a thin client with no query thresholding or prioritization. The reduced setup has clients that employ query thresholding, but it doesn't have a local cache or AR view. The DreamStore setup employs both query thresholding, prioritization, and caching with a simple directional prefetching strategy, the details of which you can find in the paper. So here's the read performance on the generic workload from our experiments. Query thresholding reduces the system workload by about 3.5 times, thereby reducing the latency. The queries see a more consistent response time across the workload. And with the DreamStore setup, this performance is further improved with almost no queries exceeding the 100 millisecond threshold, which is generally considered as an interactive response. We see similar performance improvements with the IPS workload. With the simple directional prefetching strategy, we get a high cache hit rate of over 90%. So the key takeaways from this work, interface-generated query distribution can be treated as a proxy for user focus. and it can help us reduce system workload. The access pattern of objects in AR workloads are predictable, helping us formulating prefetching and caching strategies. And with these optimizations, we can provide a consistent and interactive user experience in AR. So here's some of the planned future work. So we are building client-specific view management libraries and toolkit to build AR apps that can connect to DreamStore. We want our interaction map to cover different interaction modalities, such as voice. And we want to accommodate the design and UI visualization considerations in query prioritization. Thank you so much for attending this talk. I can take any questions, or you can reach out to me. Thank you.
Can you see the slides? Oh, I'm gonna present. Yes. Okay, hello everyone. My name is Fei. Today it's my pleasure to be here and present our paper. So researching AR has mainly been special purpose. However, with the recent advancements in display technologies, recent AR displays are becoming increasingly lightweight and powerful. In the near future, they could replace mobile phones and be worn all day, displaying information that we want to see in everyday scenarios. However, there's lack of research regarding general purpose use of AR head-worn displays, especially in everyday context. In 2017, Gruber and Clix proposed pervasive AR, which refers to a continuous, omnipresent, and universal augmented AR interface over the real world. However, with augmented virtual information become pervasive and always available, they could be distracting, overwhelming, occluding real-world objects of interest and even cause dangers in everyday situations. As pointed out by Gruber, we need to address the challenges of designing appropriate information display and interaction that is unobtrusive, not distracting, and is relevant and safe to use. So to address these challenges, last year we proposed glanceable AR. Inspired by existing research in peripheral awareness and COM technology, in glanceable AR, virtual information resides at the peripheral vision to stay unobtrusive, but can be easily accessed through a glance whenever needed. It could be an effective strategy to enable a pervasive AR experience. However, to prove that the glanceable AR concept is useful, two challenges need to be addressed. First, we need to address the design challenge by designing a glanceable AR system that is usable and practical to use in real-world tasks. And second, we need to address the validation challenge to validate that such a system is acceptable to use with high-quality usability. So in this research, we attempt to fill these gaps by developing a proof of concept glanceable AR system and evaluate the system in real-world authentic use cases. Two studies were involved in our paper. In the first study, we developed a video prototype using Wizard of Oz approach to convey our visions of using glanceable AR to the broad public. If you're interested, please feel free to scan the QR code on the top right to access the video. And in the prototype, everyday information such as calendar, weather, time are displayed as compact glanceable widgets. 3 scenarios were demonstrated in the video, including working from a desktop computer, cooking, and walking outdoor. The actor wore a Magic Wand AR headset and used the glanceable AR system to assist his everyday activities. Except the glanceability feature, in which the widgets are highly glanceable, 4 other features were demonstrated in the prototype. The first one is gaze, in which the widgets minimize themselves to avoid occlusion, but once being gazed at, they expand to show more detail. And the second one is notification, in which the system guided the user to look at the widget that is drawing attention through a blinking icon. And the third one is a follow feature, in which the widgets change from word fixed layouts to body fixed to follow the actor around for on-the-go access of information. And the last one is voice and hand gesture, in which the actor interacted with the widget he's looking at through voice or hand gestures. And to understand how people perceive the video prototype, we distributed the prototype along with an online survey to online communities. And we obtained 63 responses to our survey, which covers a broad sample of participants with various backgrounds and ages. And our results show that 36 participants are willing to use the interface on a daily basis. And some respondents like the interface because of the hands-free feature, and they consider the interface more convenient and non-intrusive. But there are also other people that are worried that the interface could be distracting, invasive, or overwhelming. As compared to existing devices such as mobile phones or smartwatches, the glanceable AR system was considered easier to check information during movements. And when hands are occupied, participants also consider the system easier to check information and interact with information. In general, the prototype received relatively positive feedback from participants, but direct user experiments are required to reveal actual usability of the glanceable AR system, which comes with the second study in which we implemented a working prototype on the Magic Leap 1 AR headset. The working prototype incorporates 7 glanceable widgets, which display relevant information based on users' own personal data. For example, we have the calendar, email, task, and fitness app linked with the user's own Google account, and the clock, weather, and news widget display information in users' own region to allow practical uses in everyday scenarios. We kept the features that received positive or control visual feedback in the first study, including the gaze contingent dwell interaction to expand the widgets, the notification to inform the widgets through a blinking icon at the periphery, and the follow feature in which the user can trigger the widgets to follow them around. We also integrated customization features to the system, including customization of widget position, scale, and notification levels. In the second study, we aim to answer a few research questions. The first one is, how do users perceive the quality of user experience of the glanceable AR system in authentic everyday use cases? And second question is, when they use the glanceable AR system, for what scenarios did they consider it beneficial or unfavorable? And we then conducted a user study with 6 participants. All participants used Google services often. We deployed personalized versions of our system, and we handed the Magic Leap 1 headset over to participants for them to take home during the duration of the study. And participants were instructed to use the interface for at least 2.5 hours over the course of 3 days and maintain a diary entry to document the scenario and perception of every use session. And we collected 27 sessions of use successfully from all participants, yielding a total of use time of over 15 hours. Frequently appeared scenarios of use, including working from a desktop computer, cooking, watching TV, playing games, and attending classes. All participants gave positive responses on the overall usability of the interface. As shown in the UEQ ratings below, all categories received positive excellent score. And participants also favored individual features such as gaze, follow, and the customization feature. They all considered the interface less distracting than existing devices. And when being asked if they were willing to use the interface every day, all participants gave a positive response. And below are some screenshots from participants when they used the interface, in which they arranged the widgets around physical monitors or near a whiteboard. Based on the comments from all participants, we found that the glanceable AR system was favorable because it required less context switching than pulling out a separate device, especially when they need quick access to some information. The always-on property also makes it viable to handle unstructured inquiries that commonly happen in everyday situations. In general, our results show that the glanceable AR system has great potential for everyday information acquisition tasks. Thank you for listening, and I'm happy to take questions.
Okay, I think you can see my screen. Yes. Hi, my name is Abby Singh, and I'll be presenting the paper Story Create AR, a toolkit for spatially adaptive augmented reality storytelling. My collaborators are Ramanpreet Kaur, Peter Haltner, Matthew Peachy, Joseph Malik, and Derek Riley, who is my supervisor. And we are from GEM Lab at Dalhousie University in Halifax, Canada. And we also collaborate with Mara Gonzalez Franco from Microsoft Research. Let's consider the story of the 3 little pigs, which has 3 pigs who each build a house, and then there's a wolf that is trying to blow that house down. Now consider that we want to create an augmented reality version of the 3 little pigs such that everyone could play this story inside their home. This would require being able to adapt the story for changing locations. To do this manually would be very time consuming, as you would have to move all of the pigs, the houses, and the wolf to appropriate locations for everyone's homes. As the story becomes longer with more story elements, you can imagine that this becomes even more time consuming. To address this problem, we present Story Create AR. Story Create AR helps to facilitate the creation of what we call site agnostic experiences, which are those designed independently of the location, like in the case of the 3 little pigs. Story Create AR also facilitates the creation of site-specific experiences, which are those designed for a particular location, which is explained in more detail in the paper. Story Create AR is the first authoring tool to integrate spatial analysis techniques to facilitate the development
of virtual reality and augmented reality narrative experiences. One of several spatial analysis techniques that we use is called space syntax. Space syntax is more formally known as a family of techniques for understanding the spatial characteristics of a building. In Story Create AR, we use three space syntax characteristics, which are openness, visual complexity, and visual integration, which all describe a type of space. In the images shown, the high values of the space syntax characteristic are represented in red, where the low values are represented in blue. Oh, sorry. Openness refers to how open a space is. In the image, the large room has the largest openness, which is represented in red. Visual complexity refers to how much you can see from one point in space. The best way to understand visual complexity is comparing a field to a forest. So a field is wide open. In the forest, you have lines of sight where you can see a large area. And the high values are shown by the hallways because you can see a far distance. Visual integration roughly refers to how visible a node is to all other nodes. So it's roughly the centrality. We also use several other spatial analysis techniques in Story Create AR, which are room-based analysis, F-formations, and proxemics, and these are all described in more detail in the paper. We collaborated with several media studies students as case studies. We worked with 3 Dalhousie University media studies students as authors whose stories motivated the design of Story Create AR. I will discuss one of these case studies in the presentation today. Tori authored Tyson's Peak, which is a murder mystery story at a cabin with a group of friends on a ski trip. For Tyson's Peak, we took a developer-driven approach, which is that a developer took Tori's story script and implemented it using Story Create AR and implemented any other story-specific features themselves. We learned several lessons with this case study. First, we learned that we need the ability to place avatars in a conversation. We need to be able to add dialogue to that conversation. We need to be able to group and manage assets, and we need to be able to create and assign animations to avatars so that they appear more lifelike. We also identified the need for generalized event management to progress the story. For example, we need to be able to move an avatar from one location to the next, which we call a traversal event. Now we'll look into an overview of Story Create AR. We begin the process at the top left with the author's story. The author uses the Story Create AR user interface to create and edit story elements, to create story events, and then to generate placement for those story elements and events. From there, the author can test the experience in augmented reality or virtual reality. This process is reiterated until the author is satisfied. Through our case studies, it was clear that the space syntax characteristics were difficult for the authors to understand. Therefore, we created higher-level placement rules that we call attributes, which can be used instead of the lower-level space syntax characteristics. For example, the author can use a hidden attribute to place a story element in a difficult-to-find location. Here's an example of an avatar being placed in a hidden area, which is defined as an area with low visual complexity and low openness. I will show how story element on the following slide can be dynamically updated to different locations. So here is one location at Dalhousie campus called the Mona Campbell. The story elements are placed based on attributes that were specified in the interface. And now we can see that they can change locations to another map at Dalhousie campus. This is the Goldberg map, and then we can view how it looks in 3 dimensions. To demonstrate the usefulness of our tool, we present a demo of one of our case studies, Tyson's Peak. This demo takes place in virtual reality using a location of a building on Dalhousie campus.
Oh, hello. Our castaway has decided.
No, I'm not gonna kill anyone.
You don't even know what you're talking about yet.
I'm not really doing too great. I think I'm gonna turn in.
And thank you for listening to our presentation.
Yes, hello again. Thanks to all the authors for the... sorry. Yeah. Hello, thanks to all the speakers for the excellent presentations, and we will have a few questions and answers now. So I think all the participants can see what questions have accumulated in the Discord server, and I'm going to select some of those now. So our first question is about the 3D curve creation. Have you tried to construct surfaces from the network of curves?
Thanks for your question. We have not tried to construct the surfaces from the 3D curves created by our system so far, but I think it is an interesting point since 3D modeling is one of the potential and interesting application of our system. So we are considering to construct the surfaces from the 3D curves created by our system to create some 3D printing or 3D modeling tools. So that is the answer of my question.
Okay, thank you.
Thank you.
So here's one more.
Yeah.
What changes if you use the bare hand instead of the phone? I mean, you could assume you have a phone that you put on the table and it's, you know, sensing everything. So you use your finger or your hand.
If we does not use the hand, the mobile device is just the static. So we cannot create the 3D curves, use the mobile phone, right?
Yeah, no, I meant in terms of usability. I mean, assume that the phone can sense everything despite it's static because it has a 3D camera. Yeah, then you could use the hand, but then does the usability change?
Oh, so you mean use the hand to create the curves and take the phone on the table? I think it's also a potential solution to the problems, but using the hand have the requirements that maybe we need to track the hand in 3D space. So in current implementation, we only consider to use the mobile device, but hand tracking will be also available to create the solution.
Okay, thank you very much.
Thank you.
So I guess we move on to the second paper now. And I have a question. So this is the paper on egocentric depth estimation and maritime navigation. So one question is, are the results on distance estimation and matching similar to real world tasks that do not involve AR? Can you say something? Do you have any hint about that?
Thanks for the question. So as far as I know, there is a misestimation in the real world too when participants are asked to proceed to say the depth estimation. And there's a underestimation in short distances and an overestimation in large distances, as far as I know. So our results contradict the real world. But we used a perception matching task experiment to assess the depth. And in this case, the participants have to perceive the depth of a real object and of a virtual object. So the depth perception of the real object is already influencing the results. So I think that it's really hard to say if it's matching or not, because it's influencing each other.
Okay. Yes, and then there is another interesting question from Pablo Figueroa. Have you shown your system to actual captains in ships? What did they ask you to do next?
So there is no actual system yet. So this was our first study about the depth perception, just to the foundation to build on. Yeah, but we have captains in our project and they know what we are building and they're pretty excited. And I think that they want to see the next prototype, the first prototype, basically.
Okay, so I'm very interested in seeing that myself. So I had another question about your study, which is your environments were very bare, probably like the sea is mostly empty except for a few ships. But what happens if you have clutter?
So do you mean clutter?
Occlusions and a densely populated environment. Would that have an influence?
I think it would have a positive influence. So if you have occlusion, that is a very important depth cue. So if you manage to have occlusion models of the real world or something like that, and display the virtual content with occlusion, that would be really helpful, I guess. Yeah, does that answer your question?
Sure. Yeah, okay. Thank you. So I guess in the interest of giving everybody some time share, we move on to paper number 3, which was about the question whether we still need physical monitors. And we have a question here, as definer, would optical see-through displays without controllable opacity also be problematic for environments in which there is motion behind the virtual monitors, e.g. open space offices?
Yeah, hi, thanks for the question. Yeah, so that's definitely something to consider. I mean, you can have virtual monitors both in AR or VR. I guess the main difference here is that if you're working in VR, you're probably working alone, isolated. And if you're working in AR, you'll be able to interact with your coworkers. So I think in the future, the question will be, what do you want to do? And it would be ideal, I think, to be able to transition between both, because distraction would definitely be a problem. Although I would say that the displays have become much better in terms of opacity. So most of the windows, the user cannot see through them. So that helps a lot as well.
Thank you. Next question by Ayush Bhargava. What were the tasks they performed? Do you think you'll get different results for something like 3D modeling?
Yeah, so the tasks here, they were all centered around answering this form, this feedback form that they had to deliver to their instructor in the narrative. So they're basically copy and pasting, typing numbers, typing a full response, cohesive response. So basically using a web browser, Office suite applications, that was basically it. I think for 3D modeling, it could be different. The whole thing about 3D modeling is that perhaps for this one, you don't want to use 2D monitors, but you can start to think of something a little bit more immersive. Yeah.
Okay, thank you. I'm really sorry, but we have to rush on because we have to stay on time. So our 4th paper was DreamStore, a data platform for enabling shared augmented reality. And Joachim Jorge asks that about the latency, as 100 milliseconds seems noticeable. Are there aggressive pre-stretching strategies that can minimize the latency?
Yeah, sure. So that's a great question. Thank you. So actually, with our platform, if you see the actual central measures, we consistently saw response times in the order of tens of milliseconds. and the standard error was like less than 5 milliseconds. We treated 100 milliseconds as a constraint because that's the number which is widely used in the interactive visualization literature. And yeah, we can use more aggressive prefetching caching strategies. They'll all be bound by the client device's memory. So it's a choice between like how much details you want to show and how many objects you want to keep in the cache at any time.
Okay, so very quick additional question. I'm wondering how strongly human users notice the difference as queries are, as you're enhancing the queries.
Yeah, so again, thanks for the question. And that depends on the actual use cases, the setting it's being used in. So we consider that as like one of the control knobs to determine what should be the threshold for the number of queries on any object for it to be considered to be ignored. And we had a user study that's not included in the paper for very, but what we asked users was basically use this app with Dreamstore and without Dreamstore. And the objects that you are trying to query in the space, how many of the objects that you are actually interested in or trying to focus on is being visualized by the interface, and how many objects that you are not actually interested in, it's just appearing as clutter. So what we noticed from that study was most users were able to see most of the objects that we're interested in with the Dreamstore setup, and without Dreamstore, they saw a lot of clutter, basically objects they were not interested in, which were in the periphery, still being visualized by the interface.
Okay, I see. Thank you. I guess we move on to paper number 5, which was about glanceable AR interfaces. And we have a question from Bing Liu asking, does the user experience cyber sickness after using glanceable AR for a long period?
That's a good question. So we didn't measure cyber sickness in our experience, but through our interview with participants, we didn't really receive any feedback about them experiencing any cyber sickness. Yeah.
Okay, and we have another question by Joachim Hoge, this which is about scalability. So how much do you think this approach can scale up?
Yeah, thank you for the question. So in its current state, I think maybe not. So in our second study, I think the always-on property of the interface actually received some criticisms from participants, and like they wanted to have certain widgets turned off when they don't need them. And also current AR displays have like limited field of view, which means that users have to turn their head more to be able to see the richer information that they need. But I believe this won't be an issue for future AR interfaces, for future AR displays. But I think another way to scale up the glanceable AR approach is to use context, some level of like context detection, so the system can be aware of the context that the user is in to maybe change the color, the shape or level of detail in the glanceable widgets to allow more unobtrusive information display, if that answers the question.
I see. Thank you. So our last paper was Creator, which is a toolkit for spatially adaptive augmented reality storytelling. And we have a question from Nermin Shalat. I heard that it was using some facial recognition, or is this wrong? And are many people experiencing the story at once? So these are actually two questions.
So Story Creator doesn't use any facial recognition. As for experiencing this, many people experiencing the story at once, right now it'd just be one person experiencing the story, but I think that would be a good future work to go for.
Okay, thanks. And Bodhi Bobenheimer asks, how is the space syntax computed? Do you scan the environment with an AR device?
So the space syntax is computed through a tool called DepthMapX, which is used to compute the spatial properties of a building. So we use a command line interface in order to utilize depth mapx. And it just takes in an FBX file or like a 3D model of the environment that you want to use.
Makes sense. Well, looking at the clock, I'm afraid we have to stop now, always when it gets interesting. So in the interest of time, I would really like to thank all the speakers. Thanks, great job. And I think the audience has your chat address or is able to follow up with you at another time, even though we have only virtual coffee breaks. Thank you very much, everybody.
to the session on emotion and cognition. We have 6 papers in this session, and the way that it's going to work is we'll have all 6 presentations, one after the other. Please type your questions into Discord, and after the 6 presentations, we'll have a question and answer session. So our first presentation will be a paper entitled Self-Illusion, a study on cognition of role-playing in immersive virtual environments, and it will be presented by Shang Ku. So Shang, you can share your screen.
Thank you. Hello, everyone. This is Xiang Gu from Peking University. It's my honor to present the paper Self-Illusion, a study on cognition of role-playing in immersive virtual environments. So what happens when we role-play in virtual environment? Research have proved that the participants would experience several illusions. The first one, place illusion, PI, an illusion related to how the user perceives place. PI is generally used to indicate the illusion of being there. The second one, plausibility illusion, PSI. It's an illusion that what is apparently happening in the virtual environment is really happening. PSI provide correlations between external events and the user's own sensations. According to Slater's work, PI and PSI are orthogonal and can both cause users physiological and psychological arousal, evoke a physiological response similar to the one that would occur in the corresponding physical world. Beyond that, however, is a question of whether there is a novel illusion when a user behaves in a virtual role that differs from the user's self in the physical world. In other words, do humans perceive themselves or as the role in the VEs? Here we propose a new illusion, self-illusion, an illusion of self-concept. Self-illusion is a generalized illusion about one's self-cognition, eliciting a sense of being associated with a role in a virtual world, despite sure knowledge that this role is not the actual self in the real world. For example, when a user plays a cat in a virtual environment, he may think that he is a cat and interact with the VE according to the cat's behavior pattern, as illustrated in the left figure. Here are our main goals. Validate self-illusion's existence, measure it, and explore its possible effect on user experience in virtual environments. To make self-illusion emerge, there should be an obvious difference between a role's self-concept and a user's original self-concept. Also, users should be familiar with the role. Finally, we choose cats. There are 2 independent variables in our experiment, manipulation of probability, MOP, and manipulation of self-illusion, MOS. The 2 independent variables both have 2 levels, so there are a total of 4 different combinations, and that's 4 groups. Our dependent variables are participants' actual degree of probability illusion and self-illusion. We designed the questionnaire to measure the dependent variables. The questions measure sense of embodiment, place illusion, probability illusion, and self-illusion in 9 items. The first 6 items were adopted from other questionnaires, and the last 3 items were designed by us. Here are the experiment procedures. The thing is a high-level probability, high-level self-illusion one. When a participant interacts with the cat, we would record their behavior. Result. Repeated measure ANOVA were adopted for the effect of MOP. We should compare these 2 groups. The statistical results showed that they differ in items 3, 4, 5, and 6. These items focus on PI and PSI. For the effect of MOS, ANOVA showed that these 2 groups differ in items 7, 8, and 9. The results prove that our manipulation is effective and the items we designed to measure self-illusion are reasonable. Also, self-illusion differs from PSI since they affect different items. We divided the behaviors recorded during participants' interaction with other cats into 5 categories. Categories A, B, and E are classified into incoherent response because these actions are more consistent with a human's behavior pattern rather than cat's behavior pattern. In contrast, C and D are classified into coherent response groups. The chi-square test shows that participants with higher self-illusion tend to act like cats in this stage. Overall, our research extends the scope of the illusion of cognition about the self by suggesting that there exists a higher level illusion about self-cognition than sense of embodiment. That is self-illusion. This illusion is dissociated from place illusion and probability illusion. They affect the immersive virtual reality experience in different aspects. Conclusion: we successfully validate the existence of self-illusion during immersive virtual environment experience. The higher the self-illusion is, the more commitment the user devotes to the role. Thank you for listening.
Thank you very much. Thank you very much. Really interesting talk. So again, for all of you in the audience, if you have questions, please post them to the Discord. We're going to move on now to our second presentation. It's entitled VR-based student priming to reduce anxiety and increase cognitive bandwidth. And this will be presented by Dan Haas. So Dan, if you want to unmute yourself and share your screen.
All right.
Thanks.
All right. I think I need to change my camera angle. That wasn't the camera angle I was hoping for, but oh well. Can you see and hear me?
We see your entire desktop, not just the slides.
Yeah, just one second here. I'm gonna stop sharing here. Let me just. Well, I can just cover the whole desktop here. Yes. Is that okay?
Great.
Okay, my name is Dan Haas, and I'm here to present VR-based student priming to reduce anxiety and increase cognitive bandwidth. Authors Dan Haas and Ali Arya, Faculty of Engineering and Design, School of Information Technology at Carleton University in Ottawa, Canada. So our first concern was the overwhelming anxiety that we were noticing with students. Both Ali and I teach, and we noticed that students were particularly anxious, with over 60% claiming that they had experienced overwhelming anxiety in the last year. So that was an inciting motivation for us. And we took to understanding student anxiety by looking at cognitive science, how we think, learning, how we learn, obviously, because that's critical to the learning student experience, and how we live, because how we live and the use of technology has become pervasive in all of our lives. So we had many interdisciplinary insights, but the 4 most relevant ones for this study were that anxiety was understood as part of a broader scarcity mindset. And by approaching it from a scarcity perspective, if we are able to transition that mindset to one of abundance, to more positive learning mindset, then we could achieve a lot of positive benefits. At least that's what the research suggested. Had not been really done within a digital environment like virtual reality, but we felt this would be a great test. And it needed to be deployed in a cyclical priming framework, because whatever effects that we created had to be replicable and sustainable over time. And we noticed that VR was a very powerful substrate to enable the types of supraliminal priming effects that the research had demonstrated. So a supraliminal priming effect is an effect that is above the conscious level, but users may not be aware of it happening. Something in your environment that you may not be in your focus, but it will actually affect you. So the methods of priming abundance, inducing calm using meditation, increasing positive affect using VR video games, controlling attention, increasing motivation, increasing or improving the context of a situation, and just the process of repeated exposures was also a method of priming abundance. So in our theoretical framework, think of the left and right sides as processors. So you'll see that there's less cognitive available bandwidth on the left side because much of it is appropriated by routines running to scarcity, high anxiety, disproportionate thinking, and cognitive biases that happen as a result of this scarcity mindset. On the right, we have abundance mindset, which is the target, where there's more cognitive bandwidth available. The overall brain power isn't any bigger, the same processor capacity, but we've reduced that scarcity thinking, we've reduced the fear and anxiety, and we've made more available for cognitive bandwidth. And our transitional interim, the diagram in the middle is the cyclical priming methodology. Based on those insights, we advocate for priming techniques, and those priming techniques are rep, pep, pop, and mop. I'll talk about those in a second. So a preparatory experience prime is something that happens before the event. Could be a VR game or a nature walk. Reflective experience prime could be a simple question that's presented after the context of the concrete experience. You have a motivational oriented prime, could be as simple as a motivational message, and a context oriented priming, which is anything in this space, particularly the virtual reality space, that changes the mindset. It could be making it more creative, using unique avatars, embodiment, or lighting. So here we are applying to the experiential learning cycle. So each of our intervention techniques or priming would happen at various points in the cycle. This is the same idea presented within virtual reality. So we drew upon the virtual reality exposure therapy idea that uses habituation to repetitively expose negative situations. In this case, we repetitively exposed positive affect-inducing things and had a similar positive effect. Okay. So the study was VR-based student priming to reduce anxiety and increase cognitive bandwidth. The top view was the view of the meditator from within the head-mounted device. The bottom view was a video game called Beat Saber, which was incredibly fun and universally enjoyed. So the intent was, while it had validation within the real world, if we can say that, we wanted to see if it was transferable and we could use scalable VR environments to be able to do the same thing. So it was a 2x2 mixed method designed between and within subjects. We had a priming method of game versus meditation. Conditions were prime versus no prime, and the dependent variables were anxiety and cognitive bandwidth. We used the state trait anxiety inventory and the University of California matrix reasoning test for our tests. And overall, as you can see by the results, the anxiety and the anxiety for both meditation and gaming showed a considerable drop, almost 20% drop. So that was positive. And if we look at the game priming, the cognitive scores were up almost 25% in the gaming situation and were flat in the meditation situation. We also wanted to get a sense of high anxiety versus low anxiety users. How were they affected? And while we did see some suggestion that there was some effect, it was not statistically relevant. So we were able to, you know, yeah, there was some value. So at the end, both VR priming conditions did reduce anxiety. The VR video game increased cognitive performance. The VR meditation condition did not increase cognitive performance. And we saw no significant difference in high anxiety versus low anxiety users. So that's our presentation on behalf of Dan Hawes and Ali Arya. Thank you. and the slideshow.
Thank you, Dan. So our next talk is entitled Exploiting Object of Interest Information to Understand Attention in VR Classrooms. And it's going to be presented by Philip Stark. So Philip, you can share.
I can only share my screen if Dan stops sharing.
Oh, sorry. 1 second. Let me just stop sharing. There it is. All right, sorry about that.
Perfect. Okay, now you should see my screen. Okay, hello. It's a pleasure to be here today. As you've already heard, my name is Philipp Stark. I'm from the Hector Research Institute in Tübingen, and I'm very happy to present our paper, Exploiting Object of Interest Information to Understand Attention in VR Classrooms. Let me give a quick motivation. In education, incidences like the COVID-19 pandemic has forced us to search for digital alternatives. So virtual reality could also be imagined in the field of education and learning. But therefore, research in virtual classroom becomes necessary. Also, several studies in educational research indicate that peer learners are an important component of motivation and learning. So we wanted to study this aspect in our virtual classroom. Another key aspect is that VR gives us the opportunity to systematically study classroom effects and use it as a tool for experimental research. But to exploit the full potential of VR learning environments, we first have to understand how children experience and behave in these situations. And in particular, our research may contribute to the understanding of how visual attention relates to social dynamics in virtual classrooms, and also includes significant consideration for the design of virtual learning spaces. So let's have a look into our VR classroom. And also includes significant consideration for design of virtual. The whole virtual lesson took about 40 minutes. It includes phases in which the teacher explained the lecture content and interactive phases in which the virtual student answered questions. In addition to the teacher's explanation, the content was visualized on the screen. And in this virtual classroom, we wanted to find out how children distribute their attention when experiencing different classroom manipulations. So therefore, we introduced 3 different classroom manipulations in a 2x2x4 between subject design. So first of all, participants were either seated in the front or in the back of the classroom. Furthermore, the visual appearance of the peer learners and the teacher could either be more cartoon-like or more realistic. And additionally, we manipulated the hand-raising behavior of the virtual peer learners. So this means when a question is asked, either 20, 35, 65, or 80% of the peer learners raised their hand. And we used this manipulation to create different participation levels of the peer learners. For our analysis, we had eye tracking measures from 280 school kids from the 6th grade. And to measure their attention, we assessed the gazed object by raycasting participants' combined gaze vector and tracked the hit object. So we could find out when and how long participants had looked at certain objects in the environment. For the later analysis, we set a visual attention threshold of 200 milliseconds. And we focused on 3 objects of interest only, namely the virtual peer learners, the teacher or the instructor, and the screen. And we analyzed the time spent on these specific objects of interest for different classroom manipulations in a 3-way full factorial non-parametric ANOVA. So let's have a look at our results. So for the attention time on the peer learners, we found a significant difference between the sitting position of the participants, with more attention towards the virtual peer learners when participants were seated in the back of the classroom. Also, virtual peers attract significant more attention when they were visualized in cartoon style than in the realistic style. For the hand-raising behavior, we expected a linear increase of attention towards the peer learners, but only found mixed results. As it turned out, in the extreme hand-raising condition, namely the 20 and 80%, participants spent more time on the virtual peers than in the more moderate 35 and 65 hand-raising condition. Regarding the attention time on the instructor, we found also a significant difference for the different sitting position. But here it was that people seated in the front spent significant more time on the instructor than people seated in the back. Also, participants spent more time on the realistically visualized instructor than on the cartoon-like ones. And once again, for the hand-raising behavior, we did not find clear linear results, but it is also worth mentioning that attention time on the instructor showed a reverse pattern than attention time on the peer learners. Also, attention time on the screen showed similar results to attention time on the teacher. This is why it is not displayed here. So looking at the visual attention in VR classroom, we can summarize the following. Participants seated in the back spent less time on the teacher and screen and more time on the peer learners, and also vice versa. Cartoon-style peer learners attract attention of the participant, and for the hand-raising condition, we found mixed results, but we also saw that participants spent longer time on their virtual peer learners when confronted with the extreme hand-raising condition in comparison to the more moderate ones. So what can we conclude from that? So first of all, in general, virtual peer learners as social actors in the classroom influence children's attention. We have shown that the distribution of attention in a VR classroom also depends on social factors like hand raising and teacher-classmates interaction. Then we found that children sitting in the back of the classroom were more easily distracted by their classmates, and different visualization of the virtual characters influenced children's attention. At the moment, we do not know how these factors contribute to children's motivation or learning, but we are looking forward to further investigate that. So thank you for your attention, and if you have any questions, don't hesitate to ask me later or email me.
Thank you, Philip. Really interesting talk. So our next presentation is entitled Evidence of Racial Bias Using Immersive Virtual Reality, Analysis of Head and Hand Emotions During Shooting Decisions, and it's going to be presented by Tabitha Pack.
Thank you, Vicki. Can everyone see my slides?
Yep.
Great. All right. Shooter bias is defined usually using two measures. One, accuracy, that people are less likely to shoot at white men if they are unarmed, while being more likely to shoot at Black men if they are unarmed. As well as latency, that people are more likely to shoot more slowly at white men if they are armed, while being shooting more quickly at Black men if they are armed. This has often been measured using keyboard and mouse, where participants would press keys to either make shooting or non-shooting decisions. And we were interested in investigating the efficacy of shooter bias in immersive virtual environments. To do this, we put people into an immersive virtual environment, which was a dark alleyway with noise. And we gave people a full body self-avatar that moved with them. The avatar held a virtual gun that they raised toward other avatars in the scene. And the avatars were either Black men or white men. Participants were asked to either shoot at armed avatars or to inhibit shooting at unarmed avatars. After each trial, they then would lower the gun back to their hip to reholster it for the next trial. From these results, when looking at accuracy and latency, we did not find the traditional shooter bias patterns. This was likely due to ceiling effects on accuracy, where our participants were overall very accurate with avatars. And also because we gave people the chance to actually draw the gun toward an avatar, adding more latency to the shooting time instead of having to quickly press a button. We also measured implicit bias, and looking at this, what we see is that we have pro-white bias as positive scores and pro-Black bias as negative scores. This measure indicated that we actually had a pro-Black population, meaning that people demonstrated a pro-Black bias as seen by the scores mostly below the no bias line. This measure was taken after our experiment, and this experiment was run during when the Black Lives Matter movement was very prevalent in the news, likely priming participants. But in addition to looking at the standard measures, we also looked at the hand motion data as well as head motion data to determine if this would be an additional way to predict implicit biases. To do this, we used principal component analysis and calculated a P95 score per trial. And more details about how this score was calculated can be found in the paper. What we found was that for high P95 scores, you can think of this as having little variance in your movement, while a low P95 score can be thought of as having big variance in your movement. This is because the high score is defined as having more movement explained by fewer principal components, while a low score is that less movement is explained in fewer principal components. To investigate how these hand and head motion bias scores related, we looked at bias where it's defined as having our white avatar trials minus our black avatar trials. And this is replicating how the implicit association D score is calculated. And what you can see with this is that for positive scores, you can think of this as having white avatar bias, meaning participants were more accurate on white avatar trials compared to black avatar trials. While a negative score would be a black avatar bias, where people were more accurate on black avatar trials. Same thing with hand bias. A negative score indicates that there is less variance with black avatars, and a positive score would indicate more variance with black avatars. What we found was that there was a significant correlation between the hand bias and the accuracy bias, such that more variance with black avatars indicated higher accuracy on white avatars. The same pattern was also seen in the head bias data, where as accuracy increased against white avatars, more variance was detected against black avatars. Finally, when looking at the implicit association D scores, we again see the exact same pattern, that as your implicit association moved toward pro-white bias, your variance against black avatars also increased. So in conclusion, what we found was that shooter bias did not replicate in virtual reality the way that we had expected. However, we were able to predict racial bias by looking at these head and hand movements. What we're suggesting here is that this is really a foundation for assessing implicit bias in virtual reality using these nuanced measures of head and hand motion. But also that this data can be used to detect behavior differences in general for avatars in environments.
Thank you, Tabitha. Really, really thought-provoking. So our next, our fifth paper in the session is titled Virtual Morality, Using Virtual Reality to Study Moral Behavior in Extreme Accident Situations. And this is going to be presented by Julia Benvegnu.
Hi, I'm Julia Benvegnu, a PhD student in Brain, Mind and Computer Science, Padua University. Today I will present a case study on people's reaction during moral dilemma resolution in driving scenarios. Moral dilemmas like the trolley problem have been widely employed to study how people decide between two ugly and desirable options. And in recent years, they have been adapted to a virtual reality administration and to more practical scenarios, such as the autonomous driving context. Understanding how people act when facing accidents involving unavoidable collisions has important implications for the design of a decisional system of AVs. However, despite the effort spent by previous study in understanding people's preferences, consumers remain skeptical about AVs. In this light, two important points need to be considered. First, the experience of being the actual driver making a choice in an extreme accident could be different compared to the experience of being in an AV facing the same situation. And second, while most studies focus only on behavioral results, considering the emotional reaction could help in obtaining a more complete view of a driver's experience. To fill this gap, our case study aims to investigate the behavioral and emotional reaction in an autonomous driving mode and in a human one, which is to focus on two moral dilemmas: a revisited trolley problem, so a 3 versus 1 situation, and an elder versus child case. We also included non-moral dilemma situation to investigate the driver experience more common driving condition. We've also chosen to overcome the typical dichotomy of the dilemma by leaving the participant a third possibility, to not pick any of the two roads and instead crashing the vehicle by going straight on an obstacle at the end of the street, sacrificing him or herself to save everyone else. For our case study, we recruited 15 participants, 8 male and 7 female, with a mean age of 23 years. The virtual scenario was built with the Unity platform and administered through the HTC Vive Pro headset. Participants were instructed that they will have to drive a vehicle that could shift driving mode from fully autonomous to human. In the human driving mode, signaled by a flashing red light, but we have to choose the car's direction, and after every single action made by them or by the vehicle in the autonomous trial, they will have to evaluate the perceived responsibility, acceptability, arousal, and emotional balance related to the choice, using a 9-point scale administered directly in the virtual environment. After finishing all the trial, participants completed the presence questionnaire and the Marlon Cross social desirability scale. Behavioral results showed that in the human driving trials, all the participants sacrificed one man to save 3 lives, and most of them preferred to kill the older avatar to save the younger. Additionally, we found longer response time in moral dilemmas compared to non-moral ones. Regarding the post-experiment questionnaire, we found that participants perceived the virtual scenarios highly immersive. However, we also found that participants with high social desirability score, which denote a tendency to present themselves in a favorable light, reported a lower sense of responsibility for action made in human driving mode compared to participants with low social desirability scores. Post-trial evaluation showed an increased sense of responsibility in human driving mode compared to the autonomous one in both moral and non-moral decisions. Concerning acceptability, no effects of a driving condition were found. We only found an higher acceptability for action that did not involve killing someone. Regarding arousal, participants were more emotionally activated when they had to deal with moral decisions in human driving mode compared to the autonomous one. And finally, we found an increase in unpleasantness in moral dilemmas resolution in human driving mode compared to the autonomous one, and an exact opposite pattern for non-moral situations. To summarize, an accident situation involving the death of someone, being the actual driver was perceived as an intense, stressful experience. More than being in the same situation, the more passive autonomous driving mode. This result could be related to the perceived sense of responsibility. The inability to interfere with the action of a fully autonomous vehicle may have made the driver feel less responsible for the consequences of that action, with a consequent decrease in emotional response. We also found an higher negative balance in non-moral dilemmas in autonomous driving mode compared to the human one. This suggests that only situations with very negative outcome, such as moral dilemmas, people find it less unpleasant to let the car act in their place, while in simple neutral decisions, like the non-moral dilemmas, they prefer to be the ones to decide. This result could be due to the loss of agency that characterizes the autonomous driving condition, and that the possibility of exact control of the environment is a fundamental need for the individual. Overall, our results outline an interesting point for AV's design. Currently, semi-autonomous driving systems are designed to act autonomously under normal driving conditions, but the driver has to regain control in the event of a critical situation, while our participants prefer the exactly opposite scheme. The acceptability assigned to the action was not influenced by the driving modality, but only by the moral content supporting previous study. And finally, we found a strong tendency to act in an utilitarian way, but avoiding self-sacrifice actions. This finding fits into the broader debate on allowing AVs to sacrifice their passenger to serve more pedestrians. Previous works found mixed results, with the survey and VR study with simple dichotomy situation or with no time constraint showed a higher tendency to self-sacrifice, while in our case, we let a limited time to act, and we give more possibility for action to the participants, but future research should analyze more in depth of this topic. In conclusion, our main results show that the principal differences between human and autonomous driving modes are at the emotional level and in the perceived sense of responsibility. They also highlighted the importance of considering not only moral dilemmas, but also more common driving situations. Future study on this topic could help to better understand people's reaction to this, and possibly to gain insight on how to increase trust in self-driving vehicles. Thank you for the attention.
Thank you so much, Julia. And the final paper in our session is entitled "Don't Worry, Be Happy: Using Virtual Environments to Induce Emotional States Measured by Subjective Scales and Heart Rate Parameters." And it's going to be presented by Jan Nicholas Voet Antons.
Correct. Thank you very much. Welcome to the presentation of our research results. My name is Jan-Niklas Voet Antons, and I will present our paper. This is a joint work by a few colleagues of mine, Robert Spang, Tanja Kujic, Luis Meyer, Maurizio Vergari, and Sebastian Möller. I'm presenting today our team effort. So what was the motivation? So the motivation was that, besides VR technology in general is increased in usage, also applications, let's say, with the focus on health-related topics are increasing. And many different scenarios, being meditation or relaxing environments, are used to, for example, calm down people or to control certain emotional states. And we ask ourselves, okay, how to bring participants in a certain controlled emotional state to then be able to test how we can influence changes through relaxation, for example. And for this, we used a stressful game in the beginning to bring people to a certain negative and high aroused situation, to then afterwards try to use a relaxing stimulus to calm people down afterwards. For this, we came up with basically 4 research questions, and one would be, as I described now, can we use a VR horror game as a stimulus to induce this high aroused and low valence states? And can the exposure in a relaxing nature environment be reproduced for a virtual environment in terms of relaxation and usage of VR technology? The third one is we had different level of interactivity. So how much interactivity the user can have with the virtual environment. This was done by instruction here. And we asked ourselves if that has an impact on how present the users feel in the environment. And the last one is if the interaction possibility also influences the emotional change, also measured as arousal and valence in this case. So there is a lot of related work available, and so VR on the one hand is quite often used to use, let's say, standard data from the psychological domain to evoke certain controlled emotional stimuli, but of course it's not limited. And one possibility to explain the calming effect of natural environments also in VR is the attention restoration theory. And with this theory, there are two types of attentional flows. One is indirect flow of attention, and one is the directed flow of attention. And in those nature environment, it is assumed to have a higher impact of this non-directed flows, and therefore a relaxation can take place. And but of course, our motivation, or in combination with our motivation, would be nice to provide this natural experience at the homes with virtual environment system. What did we use? So we had the Oculus Quest as a head-mounted display, and then we selected the Nature Tracks VR app as a relaxing environment, and we had the VR game Dread Halls as a high arousing and low valence, rather stressful stimulus. What did we measure? So we had two subjective measures, as some of the presenters before, a two-dimensional emotional assessment scale, a pictographical scale, the self-assessment mannequin, with the dimensions arousal and valence, and then we had the I-group presence questionnaire to assess presence on spatial presence, involvement, and realness. And as a third measure, we had heart rate related activity, beats per minute, and heart rate variability. And for this, we used the polar chest strap to measure this. Today, or as the last thing, how did we measure it? Basically, we had a within participant design, so repeated measure, and each of the participants went through different steps. So in between having measures as a baseline before the actual condition and after the condition, we had in between always a horror game stimulation, and then the experimental conditions being spread out, starting from a control condition with no interaction possibility to the more extensive interaction possibilities. I would today want in this short presentation just to show two results. One would be that we can clearly see the change from baseline to the horror game in the rated arousal state. So we have an increase of arousal and then a decrease afterwards again. And an opposite effect for the valence. So we have a higher valence before the horror game, and then a lower valence after the horror game. So seemingly we have an impact with a controlled impact with the horror game on the incoming state. And then also we can see that the VR nature environment in both cases for arousal and valence had the intended effect of calming people down, having a lower arousal and a higher valence. And the last thing is that we did not find any effect of interaction possibility, but we could see that through the higher interaction possibility, we had a higher sense of presence, which is clear. That brings me to an end. Thank you very much.
Thank you very much, Jan Niklas. So we now have 60 minutes for Q&A, and we have so many questions in the Discord. There's no way we're going to get to all of them. So I think what I'm going to do is just start with the first paper, and then maybe ask like one question from each paper, and then cycle around. And then I'm going to rely on the authors to go in and answer the questions if they can't have it. They've been doing a great job of that on Discord. Okay, so Sheng, we have a number of questions. People were super fascinated by this self-illusion. And oh gosh, I'm just gonna pick one at random. So Rick Scarbus is wondering if you can talk a little bit about the system characteristics that help support the self-illusion. You know, are there certain characteristics of systems that are more or less versus supportive of people achieving the self-illusion?
In our experiments, there are two factors we think can influence self-illusion. We insist that the corresponding mini games with the tutorial video, because in the video they are catching mice, they play the tissue, and in the mini games they're doing the corresponding mini games, and the avatar personalization, they can choose their own avatar. The two factors jointly affect the self-illusion, but we do not do the quantitative measurement for their individual effect. So we will do further research on the individual effect, and more factors affect self-illusion. Thank you.
Thank you. So we have more questions, but we'll come back to them. I want to give a question to Dan. So Dan, let's see. So Nirman Shaltot was asking. I can see the goal was reducing anxiety in general. How did you measure anxiety? And also, did you use the already existing game Beat Saber not as an inspiration and make your own game, or did you use the Beat Saber game itself? An implementation question.
Good question. So we measured anxiety through the state trait anxiety inventory, which was a shorter form. There was a short form state questionnaire, and we administered that before and after each implementation. So it was the STAI. And the second question was Beat Saber. Yeah, we used the Beat Saber game. We used we actually used the demo version because it was shortened. It was about 2 minutes and 52 seconds. And we allowed participants to play that twice. There's no way we could have created anything so great. So we thought that was and generally every person that played just lit up after the experience. So that was, it was a good choice for us for that experiment. Thanks for asking.
Thank you. So Philip, let's see. So many questions. Let's see. So I guess we'll just start with the first one. So Pablo was asking about the novelty of the environment for your subjects, and how novel did people come in? Did people have time to get over the novelty aspect?
Yeah, that's a really good question. First of all, the environment was novel for the children, but before the lecture started, we gave them some time so they couldn't look around. So first of all, the teacher came in and then told them that this is not a classroom, and they can then look around and get familiar with the scene. So they did this before the actual lesson started.
Thank you. So Tamitha, wow, you have so many questions. It's hard to say. So a couple of people were asking about if you saw. Maybe you can talk. You sort of answered almost all of them, but maybe for the audience, you can talk a little bit about the results by gender and by age.
Yeah. So I guess one thing that's kind of interesting in this data that we collected was that we really tried to have a more diverse population of participants. So we ended up collecting over 101 people. One person opted to not have their data actually included in the study at the end of the experiment. And one person was removed because they just didn't shoot at the avatars, which isn't that surprising that someone made that choice. But within the data, we had just over 50% women, and we also had participants in age range from 18 into their 70s. And so we didn't find any gender differences. We did look for them, and we had a large enough population that we potentially could have found something there, but we didn't. In terms of age, there is a little bit of information that actually shows that participants were less likely to be embodied in their self-avatar based on their age. So if you were older, you were less likely to accept that avatar as yours. That could be related to the fact that all of our avatars were younger in age and appearance.
Makes sense. Thank you. So Julia, people were just jumping up and down saying this research is so important. Let's see, which of the questions? So Rochan Kao was asking about if you think the level of realism of the virtual models would affect the results, like if the humans looked more lifelike, would participants have a different reaction based on how lifelike the humans look?
It is a very interesting question. There was already a study that tested this hypothesis, but only from a behavioral point of view. And yes, I think it could be interesting to investigate if the realism of the avatar affect also the emotional reaction. So it's a good point.
Do you have any insights, just informally?
I think it could be, yeah, I have to test it, but it is possible that a more realistic avatar, and in particular in the movement, can affect the emotional reaction of the driver. But yes, I'm not so sure. I have to test it. Thank you.
Thank you. And so Jan, we have a question from Yu Yang Wang asking what features of the heart rate and heart rate variability you used for the measurement and why?
Yeah, so basically we looked at beats per minute. So this is the most broad, let's say, measure you can use. And for the heart rate variability, we use the RMSSD, so the root mean square of successive differences between two heartbeats. And so yeah, we use them as as they are a good indicator once of the general arousal. And let's say the overall heartbeat, as we all know, is quite confound with activities like movement and other things. But in a controlled setting, especially the heart rate variability is a really good indicator of stress. And stress as or in the subspace of emotional reaction is quite well measured with this, especially as our setup was focused on relaxation and stressful stimuli. So this is why we selected them, and yes, they are highly correlated with those states.
Well, the questions are just pouring in. I feel, for all of you in the audience, it's hard to stay on top of all of them, and they're all so good. So let's see. So back to Shang. People were asking about the self-illusion and how it relates to people's ability, and if people who had like a stronger self-illusion would be, say, better able to catch mice if they were a cat in VR.
Thank you. It's an interesting question. Well, to tell the truth, I'm not sure whether the user can become a better mice catcher. I think the self-cognition cannot guarantee the ability. You can experience from the cat's behavior and become a cat, but a bad mice catcher. It's an interesting topic, and we will do further research on it. Thank you.
Thank you. Okay, so let's see. So Philip, a bunch of people were asking you about the, let's see, the, okay, so Benny had an interesting question about if you have any experience in relating the results you found in VR with the results in a physical classroom, or any insights on that.
Yeah, I've heard the question, and I think this is a really, really exciting question, because the reason why we tried to analyze the behavior of the children in a virtual classroom is because evaluating and analyzing children's behavior in a real classroom is very difficult due to many different issues, like, for example, starting with privacy issues, or then how would you observe children's behavior in a classroom? You have to install cameras, and then you have maybe a bad quality of the camera recordings and so on. So this is why it seems convenient to use VR to study such classroom effects instead of looking in a real classroom. And this is why we one reason of many try to implement the research in this way.
Thank you. So let's see, back to you, Tamitha. So can you, again, a question from Benny, can you elaborate a little bit on the choice of task and the persistence of the effect?
Yeah, so the choice of task was based on psychology research looking at shooter bias. So we replicated shooter bias studies, which are, they found that shooter bias exists against men, it doesn't exist against women. And so we chose to use only looking at Black and white men, and then the avatars would either pull a cell phone out of their pocket or a gun out of their pocket. And then participants had to choose whether to shoot if the avatar was armed or not shoot if they were unarmed. So that's following directly from the psychology literature on shooter bias, replicating that work. In terms of lasting effects, we weren't trying to do any sort of mediation at this point. We were just trying to figure out, does shooter bias exist in virtual reality? And if so, how can we measure it? Once we know it exists and how to measure it, then we want to look at what are mediations and looking at prolonged effects in virtual environments. And so for that, we will dive into more of the avatar embodiment literature and behavioral changes.
Thank you. So let's see, Julia, Nerman Shalthout was wondering about, you said you were using autonomous driving, and when you were autonomous, you didn't have any control over the accident scenario. That was the question. And then sometimes there was a trial where you could control it. So Nerman's wondering if you have control, if you justify what happened more than if you don't have control.
Yes, understand correctly. Yes, we found that when you have no control, people perceive less sense of responsibility, so they accept more easily what happened, and it was more stronger the emotional aspect when you have to actually drive. So yes, so we compare this two situations.
Okay, and then, sorry, just a follow-up. Dara Higgins was wondering if you had any trouble getting ethical approval to do these experiments.
Yes, a little bit, but we found an agreement. So we didn't show disturbing images, and the scenarios went black 2 seconds before the impact with the body. So participants didn't see, yes, disturbing images. So we are okay with this.
Okay, so in my 1 minute, Jan Nicholas, Ruchan Kao is asking how you apply, what measurements you use to ensure that the participants really experience the emotions as expected.
Yeah, so we tried, or we used the self-assessment mannequin, which is a pictographical scale to measure emotional responses from users, participants. And basically we did that at several times during the experiment. So always before and after we presented a stimulus, which was intended to evoke an emotional state. So basically we can measure the state the participant is in after experiencing it, and we can also calculate the difference from before experiencing it. And that's how we measured, if we can evoke the intended states, which we did.
Perfect. Well, thank you so much, and thank you all of you. We're at 9 o'clock, and they're pretty strict about the time cutoff. So I encourage all of you to check out the Discord. There are more questions and answers there, and let's thank all of our speakers.
Okay, my name is John Quarles. I'm an associate professor from the University of Texas at San Antonio, and this is the session on embodiment. So let's go ahead and get started with our first paper. This is it's going to be presented by Thibaut Poulsoult from EPFL.
Adapting virtual embodiment for reinforcement learning. So, but first, let me introduce our motivation, which is to study full body interaction in VR. In order to do that, we use a motion capture suite to track the user movement, like on the right in the video, to animate in real time an avatar in virtual reality, like on the left in the video. But now let me remind you some key definition. So first, we have a sense of agency, which is a sense of controlling the virtual body. Then we have a sense of body ownership, which is a sense of owning a virtual body, the sense of self-location, which is the feeling to be located within one body. Finally, you need at least one of these components to have a good sense of embodiment. If you have any disruption of one of these components, you will have a break in embodiment. So movement distortion is really important in virtual reality. It consists of introducing distortion between the real hand of the user and the virtual hand of the avatar. As shown by Debaba and Kokinara for static target, it exists a threshold until users can still feel embodied while noticing the distortion. This is called the self-attribution threshold. However, there is a high individual variability. That is why we need to find the self-attribution threshold for each subject. So in order to do that, we need to conceive a calibration method for the movement distortion. So first, we need to see if this method is robust to noise, for instance, from subject answer, which can be physiological or questionnaire. We need also to have something online compatible, like feedback loop. Also to be model transfer. So what does it mean? It means once you get a model, you want to be able to update this model later across several days. And compatible with dynamic data size. So indeed, the goal is to have enough trials to have a good resolution for the threshold for each subject. So now if we look at the literature for different methods, we can see staircase psychometric and staircase plus psychometric has already been used to find the self-attribution threshold. However, any of these methods fulfill the 4 criteria. When we look at the reinforcement learning method, we can see we have all the criteria fulfilled, but reinforcement learning has never been used before to find self-attribution threshold. Therefore, the goal of this study is to use reinforcement learning to find the threshold and determine its efficiency to do so. We will also compute the staircase just to have a reference and compare the result. So now, in order to assess the self-attribution threshold computed, we need to follow 2 criteria. The first one is the robustness, which is the ability to prevent a break in embodiment when the distortion amplitude is below the self-attribution threshold. So what does it mean? It means if the amplitude of the distortion is below the threshold, the user will tolerate for sure the distortion. On the contrary, for the conservativeness, when the distortion amplitude is above the threshold, the user will reject the distortion for sure. Therefore, the ideal algorithm should be both robust and the least conservative possible. Now let's look at the distortion function, which is called the attraction well. If you look at the right, so here we have both virtual hand and real hand confounded. And when we start to go on the left, so here we can see the amplitude is increasing and we have a discrepancy between the virtual hand and the real hand. Until we reach the periphery of the target, here we can see the distortion start to decrease until being null. So here at the center of the target. Indeed, since the users are able to follow the target, we stop helping them. So now let's look at the protocol. The calibration is the first block, then we have a second block, the explanation block. And finally, we have the actual experiment with 2 blocks. Each block corresponds to 1 method. These blocks are randomized and counterbalanced. We ask only 1 question at the end of each trial to detect if the subject rejects or tolerates the distortion. This question is, I felt at least once I didn't own the virtual body. Now, if we look at the task, is really simple. The subject starts inside a blue target and then try to follow the green target. The distortion amplitude will change according to the user answer, so increase or decrease. Now, if we look at the results, so first self-attribution threshold, we can see a significant increase in the self-attribution threshold. So this one is significantly higher for the staircase than the reinforcement learning. So it means that the staircase provides the biggest threshold. So subjects will tolerate more of the distortion. The staircase seems to be the best. However, when we look at the robustness, we can see the staircase is the lowest one. So what does it mean? It means when the distortion value is below the threshold, in the case of staircase, the subject has more chances to reject the distortion. This is not what we want. On the contrary, to reinforcement learning, the subject has fewer chances to encounter this kind of issue. This is what we want. So now, when you look at the conservativeness, we don't see any significant difference between the two algorithms. So to sum up, reinforcement learning is more robust than staircase. Reinforcement learning and staircase have a similar conservativeness. Reinforcement learning algorithm is a more robust alternative than a classical staircase to calibrate a distortion and prevent any break in embodiment. The limitation are the following. To better assess the result from the staircase and compare with reinforcement learning, instead of determining one threshold per staircase, we can try to find one single threshold for all the staircase with a psychometric function and verify whether the threshold is consistent across several days. My take-home message, so reinforcement learning fulfills our 4 criteria: robust nice to knows, online, model transfer, dynamic data set. Reinforcement learning finds the self-attribution threshold for each subject. Reinforcement learning is more robust than the staircase algorithm for the same conservativeness. To conclude, reinforcement learning method should be the method to retain for future application like rehabilitation to calibrate the level of assistance. Thank you very much for your attention. I will be pleased, I will answer your question at the end. And now I would like to thank my colleagues and the co-author of this work, and thank you very much.
All right, thanks. So the next presentation is going to be with 2 presenters. It's going to be Sophia Seinfeld and Tiara Fleischner from the University of Bayreuth. So you guys take it away.
We're seeing a gray bar again, or at least I am.
Now is it now? Do you see it well? No?
Still see the gray bar. I have no idea what's going on.
I have 2 presentations. Maybe I can try to open another one. Let's see if this one works. I have to.
So odd. And it happens before I request control. So
do you see it well now?
The bar is still there, but let's work with it.
Okay. So
actually, it's getting worse.
Should I start? Okay, hello, my name is Sofia Seinfeld, and today with Tiara Fleischner, we will present you our study, Impact of Information Placement and User Representations in Virtual Reality on Performance and Embodiment. So normally, within a virtual reality scene, we need to represent the user with different types of virtual representations. Moreover, users might be frequently asked to perform a motor task while having to simultaneously detect visual content appearing in any location of the 3D space. And in this study, we tried to better understand this phenomenon. So what we know from related work is that in the normal physical world, humans tend to detect faster and more accurately objects appearing in the foreground compared to objects appearing in the background. Probably due to their ecological relevance and to the immediate opportunity they bring to interact with the environment. However, we do not know if this is also true for virtual reality scenarios. This information is also important when we try to decide where to locate different visual information in a virtual reality game or any application, right? We might want to place notifications in places where they can be detected more quickly and accurately. So the first research question we had with this study is, how is information in VR processed when it is presented at different distances that might be close or far away to the user, and at different fields of view that might be more central or peripheral with respect to the user? Also, from related work, we know that having a humanoid body that we embodied might present cognitive advantages when we compare these type of humanoid bodies to tool representations or not having a representation at all in the virtual environment. So the second question we had is, does the type of user representation, having a body, a tool, or no representation, impacts the detectability of visual stimuli in VR? And what role does user representation play with respect to the subjective sense of embodiment and mental workload? So the first hypothesis we had is, when information is presented near to the user body in virtual reality, it will be more quickly detected compared to information that is presented further away. And that representing the user by means of a virtual body would enhance embodiment and decrease mental workload compared to having a tool representation or controlling the scenario through a physical keyboard with no representation.
So to explore these hypotheses, we designed a sphere task where participants were told to look out for a red sphere appearing within their field of view. They then pressed the foot pedal as quickly as possible to indicate the detection. The sphere then vanished and reappeared a while later at another location. We predefined 32 such locations distributed across 4 distances, which we categorize as near within 60 centimeters of the user and far distances beyond 2 meters. We covered 4 horizontal angles, 2 in their user's peripheral and 2 in their central field of view. And vertically, we defined 2 angles, presenting the sphere either at eye level or elevated. Further, we designed a motor task, which we call the cube task. Here, participants were asked to select the highlighted cube as quickly as possible. As soon as a selection was made, another cube would light up, and so on. Participants performed this cube task in 3 different conditions, either touching the yellow cube with their hands, virtual hands, or with virtual controllers, or by pressing one of 4 respective keys on the numpad of a keyboard. We applied these tasks in a user study where each of 24 participants first began with a baseline condition in which they performed the sphere task alone. The sphere stimulus was presented twice at each of 32 positions in random order, resulting in 64 trials. Then followed the dual task paradigm in which participants were asked to detect the sphere while simultaneously doing the cube task. This was repeated for each of the 3 conditions, so with virtual hands, controllers, and the keyboard. And in each condition, they again did 64 trials. Throughout this study, we measured the detection performance in terms of how quickly and reliably users detected the stimulus, and motor performance by counting how many of the cubes were correctly selected. Further, we evaluated embodiment and task load through questionnaires. Our main findings include that in a dual task paradigm, visual stimuli were detected more quickly when presented near the user's body. However, detection rate was actually 100% across all distances. So while it took longer to detect a stimulus further away, it was still always noticed within a given time frame. We found no effect of condition, so user representation, on detection speed, and this effect of distance on detection speed only occurred when there was a dual task paradigm. Regarding motor performance in the cube task, we found that more cubes were correctly selected when interacting either through the virtual tools, controllers, and hands in VR compared to interacting through the keyboard. Further, we found that virtual hands increased the sense of embodiment, and the sense of control and effectiveness was stronger both for virtual hands and controllers compared to the keyboard. So from our results, we conclude that time-critical information such as notifications should be presented near to the user, in particular when the user is occupied with simultaneous tasks. However, this may only be relevant in a dual task paradigm, since when the user's full attention was available, the distance did not affect detection speed. Further, user representations that support direct manipulation appeared to be beneficial for effective interaction, embodiment, and cognitive load. And interestingly, contrary to our expectations, the type of user representation did not appear to affect visual processing. So I hope our short talk has provided you with some interesting new insights, and we're looking forward to discussing this topic further with you afterwards.
Huh. Oh, am I? Oh, yeah, sure. Sorry. Okay. So the next speaker is Eric Wolf from the University of Würzburg.
Hi, my name is Eric Wolf. I'm from Hi, my name is Eric Wolf. I'm from the University of Würzburg, and I will present you today our paper, The Embodiment of Photorealistic Avatars Influences Female Body Weight Perception in Virtual Reality. Body weight misperception is a huge topic in body weight disorders. For example, people who suffer from obesity tend to underestimate their own body weight. Our idea is to support the therapy and research of body weight misperception by virtual reality. By use of this technology, we would like to influence the perception and cognition by using embodied virtual humans. However, prior research shows that system and application-related factors can alter body weight perception. For example, in most of the prior work, we can observe a general underestimation of virtual humans. Another factor which can alter the perception is the personalization factor of virtual humans. Thaler et al. In 2018 found, for example, that when observing an avatar which is personalized, that the participant's body mass index will predict the results of body size estimation. In comparison, when observing another avatar, they couldn't find this effect. In a similar experiment, which we performed last year, we could find a similar effect as Thaler et al. Could find 2018 for their personalized avatars without using personalized avatars. However, in our study, we used embodiment, whereas Thaler et al. Did not. We created a research question: does the embodiment of photorealistic, non-personalized virtual humans influence body weight perception of virtual humans in virtual reality? For this purpose, we created a no-embodiment illusion condition and compared this condition with the embodiment illusion condition. The biggest difference was that when having no embodiment, people were just observing a virtual human in a room next door which performed movement tasks, and in the embodiment illusion condition, participants were seeing themselves in a mirror while they were performing the same movement tasks by themselves. Before I explain the experiment in detail, I will show you a video of the embodiment illusion condition and also of the no embodiment illusion condition first. So first, we had a calibration phase for both conditions where people shortly had to stand in a T-pose. Then, in the next step, people had to perform or observe body movements. Here we can see a participant observing the body movements of the person in the room next door. After the participant observed in total 5 different movement tasks, they answered some question, and one of those was that they had to estimate the body weight of the virtual human they were observing. In the embodiment illusion condition, however, people perform the body movements by themselves, and you can see here that the virtual human displayed in the mirror did perform the same movements as the participant. After performing the 5 movements, again, the participant had to guess the body weight of the virtual human. Now I want to highlight some system properties. We use the IK-based 6-point body tracking for real-time animation and also for the animation recording for the animations used in the no embodiment condition. We also induced the feeling of embodiment by visuomotor stimulation, and for this purpose we used a first and third person view realized by a virtual mirror, which you can see here in the picture. As virtual humans, we used photorealistic non-personalized virtual humans, which we created from scanning a model from which we knew the body weight and the body height and from which we could calculate a body mass index. We conducted an evaluation with a sample of 56 female participants, 28 in each condition, so we used a between subject design. Our participants were aged between 18 and 29. They all had normal vision and hearing, were German speaker, had no sensitivity to simulator sickness, no mental disorders, including bodyweight disorders, and had a body mass index in a normal range. As our main measurement, we used body weight misperception, which was calculated by the estimated body weight in comparison to the approximated body weight of the virtual human. Regarding body weight misestimation, we had 3 different hypotheses. First, we expected a significant underestimation of the virtual human's body weight in the embodiment condition in comparison to the no embodiment condition. We also did not expect a significant misestimation of the virtual human's body weight in the no embodiment condition, and we expected that the body mass index of the participants will have a significant stronger effect on body weight misestimations in the embodiment condition compared to the no embodiment conditions. Let's have a look to our results. Regarding our first hypothesis, we can confirm our expectation as we could find a significant underestimation of the virtual human in the embodiment condition in comparison to the no embodiment condition. For our second hypothesis, we also could confirm our hypothesis and could not find a significant misestimation in the no embodiment condition. Regarding our third hypothesis, we also confirmed this as the participants' body mass index had a significant stronger effect on body weight misestimation in the embodiment condition in comparison to the no embodiment conditions. Here in this figure you can see that in the no embodiment conditions the participants almost independently from the body mass index estimated the body weight, whereas in the embodiment condition the body weight misestimations were predicted by the participants' body mass index. To conclude on our results with regard to our research question, we can state the embodiment of virtual humans favors an underestimation of the body weight and leads to an influencing effect of the participants' body mass index on body weight perception. If you have any questions regarding our paper, you can have a look into our paper, which you can see here, or you can ask me now after this talk. I would like to thank the German BF for supporting our work, and here are the references I used in the presentation.
The next paper is going to be presented by Aylan Grika from the University of Paris-Saclay.
Okay, hello, my name is Aileen Rica, and I'm going to present our work, which is entitled The Influence of Hand Visualization in Tool-Based Motor Skills Training, a longitudinal study. This work is co-authored with Michel Ali and Samir Othman, and was carried out at the BIS laboratory of Université Paris-Saclay. To introduce our work, I will start by defining a motor skill as the coordination of small muscles, in movements usually involving the synchronization of hands and fingers with the eyes. The training of this skill is important, for example, in surgery, where practitioners need to effectively coordinate and manipulate tools to perform the different tasks with great speed and accuracy. Indeed, mastering this type of skill is a slow process that can only be obtained through practice and repetition. The VR training overcomes safety and ethical issues associated with the in-the-field training, but while the design of the systems raises new research questions, such as how to represent the user in the virtual environment, and whether this representation can influence motor skills training. In this work, we focus on how the user's representation can impact the training of tool-based motor skills in immersive VR. In particular, we focus on users' hands representation, since for our working domain, which is surgical training, users use their hands to manipulate tools while performing the task. To explore this topic, a VR simulator was developed, which implements a bimanual tool-based pick-and-place task, and a user study was conducted to analyze user performance after 2-week training. The study followed a pre-post retention test design with 2 training groups and a control group. The experimental training condition was the presence or absence of the user's virtual hand. We formulated 2 working hypotheses for this study. First, we hypothesized that training groups would benefit from training sessions, and we expect a significant improvement between pre and post tests when compared to the control group. And second, we expect that users can improve differently under the 2 visualization conditions. In particular, we hypothesize that the hand visualization training condition would more positively affect users' performance by providing additional spatial and hand coordination cues, which was suggested by previous research. Well, the VR prototype developed consisted of an HTC Vive head-mounted display to render an immersive first-person perspective of the simulation. We used 2 haptic devices with physical handles attached to control and provide the force feedback from the virtual tools interaction. And finally, a pair of data glass was used for tracking the user's hands and fingers movements. The task chosen was inspired from similar tasks used to train bimanual dexterity and hand-eye coordination skills in surgery. It consisted of manipulating 6 small cubes with the virtual tool from an initial position to a target position. The users were required to pick the cube from the initial zone with the closest tool, change it in the middle zone to the other tool, and place it with this last tool in the correct numbered target position, with the green sticker facing downward. They were asked to do the task the most accurate and quickly possible, while avoiding dropping the cubes. And while during the simulation and depending on the experimental condition being performed, the users were able to visualize both the virtual tools and their hand representation, or only the virtual tools. The study followed a 3-way mixed design. 26 participants were recruited and divided into 3 groups, a control group and 2 training groups. All the participants did an evaluation test on the VR prototype at the pre-test phase on day 0. They performed the task 3 times under the virtual hand visualization condition and 3 times under the tool-only visualization condition. This evaluation was repeated 2 and 3 weeks after for the post and rotation phases respectively. In addition, both training groups performed 10 daily training sessions in the VR prototype between the pre and post phases. For each training session, users perform 10 times the task or 20-minute training. And well, during this phase, one of the group was trained under the virtual hand visualization condition, whereas the other group was able to visualize only the virtual tools. And well, finally, the user's performance was evaluated through the task completion time, the accuracy of placing the cubes, which was the position and orientation, and the number of cubes dropped. Well, as for the results, well, on the one hand, the results suggest that the training of the pick and place task in our VR simulator for both training groups improves participants' time, accuracy, and errors as compared to the control group. Indeed, training groups improved between 40 to 80% their performance between pre and post phases. On the other hand, we do not observe a significant impact of users' hand representation in user training for tool-based motor skills. Indeed, we found only small, non-significant improvement concerning the rotation difference accuracy measure in favor of having the virtual hands representation. Well, as a whole, the results of this study show that while users improve their performance after training the VR simulator, showing that our simulator is effective for training the design task. However, there was no performance difference between the two training groups, suggesting that while tool-based motor skills trainers do not benefit from hands representations in terms of performance for this type of task. Well, the main limitation of this study is the small sample size of participants, which might have limited the visualization of a significant effect. And well, another limitation is that only one type of hands was evaluated, providing position, orientation, as well as finger flexion movement, but which did not contemplate participants' appearance and size. So other studies are needed to generalize these results to other forms of embodiment and different tasks. And well, finally, in the future, we also plan to include a real-world training condition to compare VR training to traditional approaches for tool-based motor skills training. Thank you very much for your attention. I would gladly answer to your questions hereafter.
So our last speaker is Sahar Asiri from the University of Minnesota.
Communication in virtual social environments. The research we present in this paper is driven by the expressed needs of our architecture colleagues for a system that supports collaborative discussion between multiple stakeholders in the context of immersive design review. The minimum standards identified by our colleagues as essential to support their needs are: first, the ability to see where each person is standing. Second, the ability to see where each person is directing their attention. And finally, the ability to support gestures, for example, pointing and nodding in agreement. Our provided solution to better support some more aspects of interpersonal communication using a more sophisticated avatar representation. We suspected that the use of video see-through technology might afford increased communication effectiveness by providing access to aspects of facial and body expressions. We used the Z-menu stereo camera with a green screen to represent the real avatar condition. To better understand the relative merits of various best available embodiment options, we ran an experiment to investigate the impact of visual and non-verbal cues afforded by 3 different avatar representations, which are no avatar, scan avatar, and real avatar, in the context of several collaborative tasks to measure interpersonal communication. Our system used 2 laptops and 2 HTC Vives for 2 users in the same virtual space, the 2 users standing and facing each other at a comfortable conversational distance of about 1 meter. To guarantee consistency, we set up the tracking space on one laptop and copied the resulting file to the other. We also used Photon Unity networking for data synchronization. In each case, the participants saw themselves and the experimenter represented using the same type of representation. For no avatar representation, the participant view of self and participant view of experimenter represented as a floating HMD with 2 controllers. For scanned avatar representation, the participant view of self and participant view of experimenter represented as a full-body virtual avatar. The experimenter body model was obtained using high-quality 3D body scan from a commercial 3D scanning company. For the participant body model, we used Make a Human to create gender-matched avatar, resized based on the participant height. with different options of skin color. For real avatar representation, the participant view of self and participant view of experiment are represented as a real-time image using the ZSTK to adjust the chroma key to remove the green screen from the capture image. We recruited 36 participants. Participants were recruited via posted flyers. Each participant was given a $30 gift card for participation. We collected multiple subjective measures such as social presence, interpersonal trust, interpersonal communication satisfaction, and communication behavioral cues. All survey responses were collected on a 7-point Likert scale. Our objective measures included mutual gaze and the count of unique words. We also conducted an exit survey to learn more about the user experience of each avatar type, including which representation they preferred overall and why. Our main hypotheses are: experiencing interpersonal communications with a real avatar will enable users to feel a stronger sense of social presence and will allow users to feel more interpersonal trust, and also will result in users feeling a higher level of communication satisfaction. Our experiment is within subject design. The experiment is involved 3 avatar types and 3 tasks, which are conversation cards, survival items, and charades. We paired a different task with each avatar to avoid carryover effects. The assignments of avatar to task counterbalance between participants using a 3x3 Layton square. Each task had a duration of 7 minutes. The social presence results show no significant differences in the aggregate social presence between the 3 avatar conditions. However, we found a significant difference for the co-presence. The post-hoc test indicates that the real avatar and scan avatar mean ranks were higher than no avatar. The results for the other subscales indicate no significant differences between the avatar types. The results for the interpersonal trust show a significant difference between the 3 avatar types. The post-hoc test indicated that the mean rank of real avatar was higher than the other 2 avatars, while the results for interpersonal communication show an insignificant difference between avatar types. The results for attentional focus and behavioral cues show significant differences were found for body posture and facial expression. The post-hoc test of body posture indicated that the mean rank of scanned avatar was higher than the other 2 avatars. Also, facial expression post-hoc test indicated that the mean rank of real avatar was higher than no avatar. We anticipated that the mutual gaze and unique words could be affected by the different task requirements. Therefore, we decided to use between-subject analysis to compare the effect of avatar types with each task. The results for mutual gaze show significant differences were found for conversation cards and charades. The post-hoc test of conversation cards indicate that the mean rank of real avatar was higher than scan avatar. Also, charades post-hoc test indicate that the mean rank of real avatar was higher than no avatar. For the unique words, we only conducted the audio analysis for the conversation cards and survival item tasks, because the charades task did not involve speaking. The results for the unique words show a significant difference was found only for survival items task, and the post-hoc test indicate that the mean rank of no avatar was higher than real avatar. Overall, in the exit questionnaire, 66.67% of participants stated an overall preference for interacting in the real avatar mode, while 25% preferred the scan avatar and 8.33% preferred no avatar. In conclusion, these findings provide novel insight into how a user's experience in a social VR scenario is affected by the type of avatar representation provided. So with that, I will thank you for your time in watching our work. Hello everyone, my name is Sahar Asiri.
So we have some questions. I'm going to try to go through this just in the order that we presented them. So for the first one is for the first page. So this is for Yuval, this is for you. So So reinforcement learning often requires collective, extensive amounts of data. How do the users feel about doing 30 minutes of repetitions?
Okay, so in the paper we have written, we have a limitation of 100 trials to be sure we don't have this kind of issue, but we will hardly reach this limitation. Most of the time the algorithm managed to converge around 70 trials, so it was less than 10 minutes, and when you reach the 100 trial, you have 10 minutes duration. So we never reach the 30 minutes duration.
Okay, next question. It seems that you use the two AFC responses as input for the UCB, but is it possible to use behavioral indicators such as trajectories of hand movement?
Sorry, I didn't understand the end of the question. What do you mean?
Oh, yeah, sure. So they're asking, you use the two AFC responses as input for the UCB.
Yes.
But is it possible to use things like trajectories of hand movement instead of the two AFC as input?
Okay, so the trajectory of a hand?
Yeah, the trajectory. Yeah, like how I move my hand.
Okay, to answer the question. So okay, so gesture recognition maybe. So to answer the question in our experiment, so they have to answer with a controller. So they select the answer with their gaze. So it might have been indeed faster if they just have to click like two buttons. But we didn't do any gesture recognition because it was each time if you have something which doesn't work very well, it's not robust. It's more cognitive load than just pressing a button. That's why.
All right. So the next question is going to be for Sophia and Tiare. Let's see. The first question is, how did you parameterize the task, thus distances and sizes of the spheres?
Do you want to take it, Sophia, or should I?
Yeah, I can take it. Well, the distances were prefixed within the virtual scene, and the spheres were resized. So for spheres that were further away, they were actually bigger, but they appear to be as the same size as the ones that appear closer. So we kept the visual angle constant, and we resized the spheres in order to be perceptually equal size. So the participants saw spheres with the same size.
And maybe to add to that, that of course contradicts the depth Q to a certain degree, as in closer objects are usually larger than further away objects. But we did actually evaluate this, and participants still felt like they still perceived the distance spheres as more distant, despite them being the same size. So their remaining depth Qs actually maintained that illusion of them being further away.
Okay, next question is, how did you differentiate the measurement of cognitive load from the measurement of task load using the NASA TLX?
Yeah, I would say that the NASA was not used as a measure of cognitive load per se to the double paradigm task, but it was only used to test whether the task load or the subscales that the NASA measures differ between the user representation. So between the tool representation, between the avatar representation and the node representation. So and we did and we saw some differences between the representations, but it was not a measure to measure the load of the task itself. So yeah, just to clarify that.
Okay, next question is going to be for Eric Wolf. So it says, I didn't quite catch the distribution of body weights among the avatars and the relationship, if any, with the participant's body weight, such as a percentage. Did you see any different trends between lower BMI versus higher BMI participants?
Yeah, I'm actually not sure if I got this question correctly, but for people who embodied the avatar, we could see the trend that when they had a lower BMI, they underestimated the avatar, and when they had a higher BMI, they overestimated the avatar. Whereas in the other condition, we couldn't find this effect. I'm not quite sure if this correctly addresses the question, but maybe we can talk afterwards more about it.
Let's see. Another question that I had, Eric, was why the specific arm movement? Because it was like this, right? So I was curious as to why you chose that specific arm movement, and do you think that a different gesture would have affected estimation differently?
Oh, actually, I don't think that a different movement would affect the estimations. Actually, we choose this movement because in the embodiment condition, we wanted to have this coherence between the movements and the picture, what they see in the mirror. And then we had to do the same movement basically in the other conditions. So the movement task was adapted from the embodiment condition.
All right, let's see. The next question is for Eileen. So it says, I was wondering if you had assessed the experience of participants in VR or video games, and if you think this could influence either the representation of the user or if it would impact the performance or not.
We ask participants in demographic questionnaire whether they had experience with VR and they play video games regularly. I use that information only to verify that my baseline at pre-test didn't have any influence on expertise of participants. However, there were we didn't have too many participants that use VR regularly, so we weren't able to discriminate into expertise using VR to assess performance in this study. But it could be interesting in a future work to see if these results change regarding this.
So another question that I had, Eileen, was did you either obtain or observe any, or maybe this is just through observation, but subjective feedback from users on what they thought about having hands versus other users that didn't have hands, and if or did you look specifically at embodiment for both of those conditions, and if so, or any kind of insight that you would see as to why they would, why you think it might have turned out the same in both, or close, right, in both conditions?
Well, I think that well, the tools are almost every moment during the experiment attached to the user, since they are using during the whole experiment. So it's like the tool becomes like prolongated. I mean, the hand gets prolongated to the tool, so the tool becomes the actual hand. So maybe that's why they do not. It does not represent too much information for the performance measures. We did a previous study concerning subjective evaluation of embodiment, agency, and ownership. And again, we didn't find a significant difference between participants' opinions.
All right, let's see. The next question is going to be for Sahar. Let's see. Could users also see themselves, like, or was there a mirror there that they could see their full body with? It says, I found it interesting that people didn't feel much difference in presence as a self-avatar, probably because you don't look at yourself that much, right? When you're interacting with someone else, so maybe they didn't notice themselves as much. Or maybe the question is, if you had a mirror so you could really see your full body, do you think that would have made a difference in your experiment?
So thank you for the question. The main goal of our study is to study the interpersonal communication with other person in the environment. So we try to make our best to make each condition has same representation for the users, same as the experimenter who do the experiment. so when I did the experiment, some of the participants, they just realized their like body movement and body like hand using the avatar or like the real avatar image, and while they experiencing some task with them. So so they have some sense of their presence in the environment, but maybe for future work, we will look at showing them like a mirror before we start the experiment.
Okay, next question is, I'm wondering whether the measurement of interpersonal trust was related to themselves or towards the other users.
To the other users.
I think they're asking like this is an interesting question, I think, because do you trust your own avatar versus trusting the other person's realism?
Yeah, we all our measurement asking about the other person.
Okay, gotcha.
Yeah. So all the question asking, do you feel trust with the other player? Are you planning to relieve some information to a personal information to the other person and so on? Yeah.
Okay, let's see. We have a couple of other questions. Okay, here's another question for Sophia and Tiare. Do you think the different input methods, such as the foot pedal versus putting your hand on the cubes, affected reactions to objects in near and far distances? And would your results change if you asked users to provide input solely via the controller?
Maybe. So this is a tough one, I think. Our intention was to choose something different, in particular, a different body part that actually provides that input, because we didn't actually want to increase the cognitive load of having to remember what key or button to press. I guess we can't give a definite answer to this. It remains to be researched in another study, but that's a really good question.
Another question that I had as part of that was, how do you were you able to qualify errors? I feel like I always struggle with this in designing studies like this, where how do you know when how often did people accidentally press the button, or do you know, are you able to tell when people accidentally press the button or
accidentally do it at the correct time? Or?
Yeah, well, or like at the incorrect time even.
Right? Well, then it wouldn't be a successful detection.
Okay.
And they had a 100% detection rate, so that.
Oh, okay, gotcha. So that takes care of that.
Okay, yeah, gotcha. No nervous trigger finger or anything like that.
Well, I was thinking more along the lines of the hands, right?
Oh, you mean touching the cubes?
Yeah. So basically, like when they reach out, if they like accidentally graze one of the cubes without realizing that they grazed one of the cubes, just because of the nature of depth perception in VR, right?
So if I remember correctly, we didn't actually register false cube selections, but it just wouldn't switch to the next one if you didn't touch the correct one.
Gotcha.
So yeah. That was, so basically what we count is correct hits of cubes, how many cubes they actually touched correctly.
Yeah, in the cubes we just counted hits, but in the spheres that was the pedal task. So in this double task paradigm, we did count when they just press the pedal randomly, but there was not a target in the scene.
Okay, gotcha. Okay, here's another question for Sophia and Tiare. Could the sense of embodiment, even with controllers, be stronger for participants who are more acclimated to virtual environments, potentially through prior experience with video games?
Do you want to answer that one, Tiare? I answer.
Sure, it's a really good question, and I wonder that myself very often. When I was developing my prototypes, like I was using them every day, and I felt like, damn it, I feel embodiment about every single user representation I'm using here. And so subjectively, I'd say maybe we can get used to our body changing. We update our body image based on that. So the thing is, I'm not aware of any clear evidence in research yet. So it's really just, my intuition would be probably, maybe, I'd guess so. if anyone can actually point to research, either confirming or denying that, please post it in the Discord channel. That would be awesome to know about.
Okay, I think that is pretty much all the questions we had. So let's all virtually thank our presenters. We get like one of those things that plays a big applause. I don't know why we don't have that yet. Yes, thank you everybody for watching for presenting and watching the session on embodiment. This was really interesting, and you can follow up with the authors and their papers in Discord, and they will continue to answer questions as you get further questions, which I'm sure will arise as you read their papers. Okay, so thanks again, everybody.
Thank you too.
Thank you.
See you.
So, hello everybody. It's my privilege to say how happy I am that our first official day of IEEE VR 2021 is coming to a close. This is the the welcome reception, which is kind of strange because there are no drinks and no snacks, and I hope everybody feels in a good mood. We are just a few words to say in acknowledgement of our sponsors, but more important than that, I would like everybody to stay tuned for the IEEE VGTC, or Visualization and Graphics Technical Committee Career Awards, hosted by Professor Henry Fuchs, who will be talking after this short intermission. And I'm so pleased that on a short personal note, I'm very pleased that we had a fantastic keynote by Betty Muller today, and that we had fantastic paper sessions. And I'm really pleased that we went on schedule and trying a new format that I hope it will be the crowd pleaser for years to come. At least the incoming VGTC, the steering committee chair tells me that he's also pleased. So good omen. Without further ado, I would like just to say that this year we have started a new format in terms of partnership with the IEEE Computer Society, and that they have been instrumental in making sure that we could afford to run the conference in this way by lining up a fantastic slew of sponsors. And I would like to yield the floor to Michelle Tubb to say a few words about sponsorships and show a short promotional video by our Diamond sponsorship sponsor, Verbella. Michelle, thank you for all the things that you've done for the conference. As a co-chair of IEEE VR, I'm very happy that we have this working relationship going for the first time.
Thank you so much for that introduction, Joachim, and thank you for allowing the Computer Society to partner. IEEE VR is an amazing and incredible event, and it can't be done without the dedicated work of all of the conference organizers. This is a collective effort and is just immensely impressive. And to just add on that, these types of events can't really happen without the support of supporters, leading companies that want to align themselves with the event and demonstrate their support of the technology and research that are taking place. So I'm happy to recognize our supporters for IEEE VR 2021 this year. And I'm going to share my screen, and hopefully now everyone can see that this year's Diamond supporter was Verbella, and followed by gold sponsors, and including the ILRN, which is where the event is taking place this year. We have Qualcomm as our silver sponsor, and a lot of bronze sponsors this year, including Vicon, Hit Labs, Microsoft, XR Bootcamp, Appen, and Facebook Reality Labs. We're so happy to have the support of our sponsors and additional supporters that donate to some of the diversity and inclusion programs and donate prizes for the event. It's all a collective effort, and we're so very happy to have the support of these great companies. And in terms of the Verbella video, they do have a 10-minute presentation that will be available on live stream, along with this,
Good afternoon,
this session
everyone.
later on. So
thanks for.
Unless you want, yeah, because it's the long presentation, Joachim, the 10 minutes. So I won't be showing the video right this moment. Thank you very much.
Okay.
Joining us this afternoon. Really a pleasure to have you here. We are here to talk about how to build a billion-dollar, or I should say multi-billion-dollar company in a virtual world. It's been a wild year with the pandemic. we've seen a ton of companies being forced to go remote. And there have been a lot of good things, right, come from it. We're finding people can be really productive remote. We're finding people enjoy being around family. They can move to different parts of the country or the world. So we're seeing a whole lot of benefits from this kind of forced remote work situation that's been forced by the pandemic. But we're also seeing some challenges, right? We're hearing about things like Zoom fatigue. We are hearing about burnout. We're thinking about how do you build culture virtually. So we have this great opportunity to continue working remote as we're recovering here from the pandemic, but we've heard a number of companies say they're never going back, right? They'll always have the option to stay remote. So today we're here to talk about a really interesting business, an eXp Realty, who's been building their business virtually in a virtual world for the last number of years. And they've actually had just incredible results through the pandemic, growing incredibly in their business. And we have Mike Vane here, who I'll introduce here in a minute, joining us as the SVP of people at eXp Realty and eXp World Holdings. But first, we're going to talk a little bit about myself and the virtual world. So I'm Alex Howland. I'm the founder and president of Virbela. We create virtual worlds for business, events, and education. My background is actually as an organizational psychologist. I was, studying organizational psychology back in 2010, 2011, and 12, and saw a real need to build virtual communities of learners online. And we've been building ever since 2012. And again, really excited to have EVP, not SVP, Executive Vice President, Mike Vane here with us from eXp Realty. Welcome, Mike.
Hey, thank you, Alex, and pleasure to be here with you and talking about the Virbela platform. eXp Realty is a 4-time Glassdoor Best Place to Work company. We are all across the globe. We have 1,000 employees with over 47,000 real estate agents across the globe. We are fully remote, fully virtual, and this is all done on the Virbela platform that we have today. And we've had a considerable amount of growth over the past 5 years, as well as through this time period through COVID here. Just a tremendous amount of growth in front of us here. And we live and we work and we do all of what we do, both as staff and as agents, all here in the Virbela platform. But you can see the space that we have, plenty of boards that we use that our staff can look up, work through the same lens of what we're looking at, whether it's some of our benefits like ClassPass or so forth. Our team members can work through that in the live in the same time. Let me.
And where are people, logging in from? Are these folks all, in a particular part of the country, across the world?
Yeah, all of the above, and that's what's great about it. I'm in the Chicago area. All of our staff are all around the globe. If we look at our HR team, there's some that are in Seattle, some in Arizona, some in Louisiana and Georgia and North Carolina, and it goes on. And our hiring practices know no boundaries for that. Being in the Chicago area, one of my challenges was always, how do I get there? What's the commute like? It was always going to be an hour-and-a-half commute down to the city, getting a train spot, making sure I caught the train, hoping that the train was on time and not late. And I don't have to worry about that. There's about 3 hours off my commute every day being able to do that. And we have zero boundaries of where we're going to recruit from, where we're going to hire from. We're hiring the best people. And that may be someone in Chicago, or that may be someone that is in the middle of the state of Arkansas, or anywhere else. It doesn't matter where they're at. We're looking for the best and to get things done And that's the beauty of it. And someone may live in a certain area, want to move somewhere else. In typical companies, that's not doable, but it is here at EXP, which is just amazing.
Things like implicit bias have been, particularly a hot topic, important topic these days. When you do your interviews, are you doing interviews actually in the world, or are you doing it on Zoom? Where are you doing your interviews?
And that's a great question. We do all of our interviews right here within the virtual world here, and that makes it amazing. Everyone that comes in can change up what their avatar is like, what they look like, and what the avatar is wearing, and so forth in there. But everyone comes into the virtual world. My avatar is maybe a little bit more fit than I am personally. So I love that, and that we are able to do that from there. But it definitely pulls down a lot of those barriers of some of the unconscious bias that can be out there in your typical live workforce in there. But everyone coming in the door, we make sure any candidate is coming through. We are interviewing within the virtual world, because this is a space that we live in every day, all day. Again, our staff, our agents, this is where we work. This is where we collaborate. This is where we get things done. And it is exciting. It's exciting that I can be sitting in a room with someone across the country. It's exciting that I can be sitting at the table of a conference room of someone across the globe, and we're getting multiple people in there. There's a sense of community of everyone across the table looking at the same thing, working on the same thing, and getting things done without having to spend a single penny on airfare or hotels or anything like that.
I think we're getting close to the end of our time here. eXp Realty started virtual, right? They've been doing this since day one in 2009 and have grown into it. It's second nature. It's so cool to pop into the world, and people don't even think about the world, right? It's just where they go to work, right? But other organizations might be thinking about, shifting from video conferencing or something into an environment like this, which is obviously goes through a kind of a change management process and getting people comfortable, familiar, working in these environments. What advice might you have for folks who might be thinking about giving this a shot?
Yeah, so most of us have already gone and done that, of going into a remote session here. I know most of my HR colleagues at other companies, as they're going and looking and saying, do they go back into the workplace? Do they go back into an office? Their time right now is spent on COVID controls, and what does that look like? And will people support it? And it's really taken away from things that are business related. And my time is spent on business related things and not COVID protocols from there. And I love that. I love it. It's one of the things that it has helped us grow even internationally, 10 plus countries during this time within COVID without ever stepping on a plane and doing that. And so the thing that I would say is we've been there. Most companies have already gone remote here within COVID. This is an additional step to really enhance what most have probably been working through remotely, is to say, now this is a step back into an office, although it's a virtual office. Most have been in where they've been utilizing video platforms, but this is really an enhancement to get back to an office, but a virtual office, and to have a stronger sense of community. And so I think the step for those that have been remote and been thinking about the step back into office, this is actually an easier step for them, and a much more exciting step for them to get a much greater sense of community here.
actually facilitated this new instance of IEEE VR in VR. And without further ado, I'd like to yield the floor to Henry Fuchs for the IEEE VGTC Career Awards ceremony. Thank you, Henry.
Thank you, Achim. Let me share my screen with you. You all see this? Well, good morning and good afternoon and good evening, depending on where you are in the world. I'm Henry Fuchs, and I'm pleased and honored to present the 2021 Virtual and Augmented Reality Technical Awards. These awards have been given for now, I think, 16 years. Here are the previous awardees. We're honored to have several of them with us here in the studio audience. Among them, Fred Brooks. Thank you, Fred. Mark Bolas. Thank you for coming, Mark. Steve Feiner. And both of last year's award winners, Jeremy Bailenson. Do I see Jeremy? And Vicky Interante. Thank you for coming. In addition, several of these people and others have graciously agreed to be on this year's awards committee. Jeremy Bailenson, Carolina Cruz Nera, who had to go off in emergency, Steve Feiner, who's here, Victoria Interante, who's here, Hirokazu Kato, for whom it's now, I think, like 1 or 2 a.m., Anatolia Couillet, and Lara Trotoy, who's taking one of her child to the emergency room as we speak. Let me say a word about the selection award process. We spent a lot of time to make this as transparent as possible. There's an entire page of details in the proceedings of this, but here are the highlights. Anybody can nominate anybody for either award. You could find this on the homepage of the conference. You could find it on computer.org, VGTC. You could write to this email address. There's lots of other places on social media. Just send in your awards. All the nominees are considered by the awards committee. There are multiple rounds of secret ballots. All the ballots are counted independently by 2 tabulators who are not members of the committee. This year, they were Tobin Asher of Stanford and Rosario Villa of UNC Chapel Hill. We take conflict of interest very seriously, so award committee member cannot vote for any nominee with whom they have a conflict of interest. For example, same institution or co-author or advisor, advisee. We use the widely used conflict of interest rules that ACM SIGGRAPH has developed. In the final round of voting, time-consuming is the instant runoff method, ranked preferential voting, which we find works very well. Finally, I, as chair, chose not to vote. A final comment is that the VGTC is in the midst of expanding the awards program, and there will be several new awards. Look for the announcements, probably a significant new researcher. There'll be a new service award, and there'll be most likely an entire VR academy. And you could look at the VGTC webpage for awards. You'll hear about them in many different places. So the 2 awards this year, the 2021 Virtual Reality Technical Achievement Award goes to David Lupke. David, let me just say a few words, has been researching and leading research teams at both the University of Virginia and for the past 15 years as a founding member of NVIDIA Research. In recognition of his research and leadership at the intersection of rendering algorithms, display technology, and Human Perception. The IEEE Visualization and Graphics Technical Committee is pleased to confer its 2021 Virtual and Augmented Reality Technical Award to David P. Lupke. Congratulations, David. Now we can clap.
Thank you so much. I'm going to share my screen.
Please.
Okay, does everybody see it?
Yes.
Okay, so I was asked to take about 5 minutes to, acknowledge the tremendous debt that I have, that I owe for this award, and all the people who've made it happen, and maybe share just a couple of thoughts on my body of work and where I think things are going. So that's what I'm going to do. First of all, I should begin and end this presentation by thanking my family, the family that raised me. This is my mom, my dad, my stepmom, two of my brothers. The third one didn't make it, so I threw all three of them on there. I'm one of four brothers. My brother Steve, Chris, and Paul. Paul's two children. And of course, the family that I'm raising, my sons Owen, Edwin, and Cyrus, who we are raising with my amazing wife, Emily. So thank you to all of the support that I've gotten and all the upbringing that I've enjoyed, and you're wonderful, wonderful people, wonderful support. Thank you. And there's so many people that one should thank. I want to particularly give a nod to three people who I would say gave me a chance. Starting with Professor Stephen Janke from Colorado College, where I was a chemistry major. I happened to see him setting up a 3D computer graphics system. It was a Silicon Graphics Indigo, if you want to place the time exactly, in the graphics in a computer lab where I was doing word processing. And I got so interested, I essentially lied my way into his computer graphics course. And I think he knew that I was lying when I said that I knew Pascal and I could figure out what was going on. But he gave me a chance. He let me into that course, and that really set me off and changed my career. And I need to thank Dr. Fred Brooks, who is on this call, as another person who saw this chemistry major from a small college in the middle of nowhere with exactly one computer science course to his name at that point, which is the aforementioned computer graphics course, and took a chance that I could succeed in what was then arguably the best computer graphics program, and certainly the most active virtual reality program when it came to hardware and real-time rendering, which turned out to be my main interest. And finally, many years later, David Kirk, chief scientist of NVIDIA, who was founding a long-term research group at NVIDIA, and again, sort of found out that I might be interested and took a chance on me and helped hire me to help him found and create this long-term research lab. So thanks to all of you. There are so many friends and colleagues and mentors at UNC and the University of Virginia and at NVIDIA. There's far too many for me to name, so I won't even try. And among those, but not completely overlapping with that said, I need to thank my team. So I run at this point a large team of 45, 47 researchers across the Western Hemisphere, and I've been co-authors with many of those people. And of course, again, this is far too many people to name. We'd be here all night. But I do hope that all of you realize that this award is really recognizing your amazing work. As a leader, most of what I do is recruit great people and get out of the way. As a co-author, of course, I'm simply part of a team, and not a single one of my papers has been by myself. Every single one has been joint work with amazing people. Quickly, I've worked on a bunch of things in VR. This award made me reflect on them. Primarily, I would say I've worked on real-time rendering, which is what I believed was the bottleneck once I arrived at UNC and saw sort of the state of VR in 1993. And so my work there has had to do with visibility and level of detail, and lately ray tracing. And a common theme that emerged after a couple of years was the idea of driving real-time rendering with some sort of perceptual understanding of the human perceptual system. And so again, level of detail, all kinds of wacky rendering protocols that were inspired by work by Henry Fuchs and Gary Bishop and Ellen Scherziger and Leonard McMillan at UNC, but grew on to do all kinds of wacky things. Much of that work was with Ben Watson, who's now a professor at NC State. And a lot of foveated rendering and foveated display. And speaking of display, the thing that I've really sort of picked up at NVIDIA is worked on all kinds of sort of interesting and again, kind of wacky displays, be they near-eye light field displays or ultra-low latency displays or foveated displays or displays that accommodate your eyeglasses prescription. And most recently, and I think most exciting, is this trend towards holographic displays. And I'll return to that theme. My final slide, I just want to predict a few things that will matter. So if you're not paying attention to these trends, if you're not working on these things, but you're in the field of VR, I think you should consider them. Neural rendering, we can make amazing pictures now. We've sort of broken through the uncanny valley in many ways when it comes to pictures of things like human beings, human faces. And that's going to be an important, and we can do it in real time. We can do it very inexpensively. That's going to be an important trend. I mentioned holographic displays. By this, I really mean phase-based displays, displays which are using the principles of wave optics to form the image that ultimately lands on your retina. I'll take a more specific flyer and I believe that extremely low power efficient implementations of 2D graphics is going to be vital for VR and AR, right? The ability to superimpose text, emoji and maps and diagrams in 2D, but spatially in place, that they have a place in 3D, whether that's, a name card hovering over somebody's head at a conference, or a map that's spread out on the ground in front of you so that you can see what direction you should walk. I think doing this within, a 300 milliwatt power budget is going to be critically important. And finally, trustworthy visual computing is the term that I'm using to account for things like privacy and trying to prevent or at least mitigate some of the nefarious things that people can do with all of these other amazing technologies. At some point, we will be doing events like this entirely virtually. We will be projecting our avatars into each other's living rooms, conference rooms, classrooms. And how do you know that it's really my avatar speaking? How do I keep somebody else from using my avatar for purposes that I wouldn't agree with? How do we ensure the privacy in a world where everything is tracked and everything from gaze to people's surroundings is tracked? I think these are critical problems. And as I promised, I'm beginning and ending by thanking my family. So thank you again for this award. It was a tremendous surprise, a tremendous honor, and I'm very excited to be here. Thank you.
Thank you, David. I should ask, do you all see my screen?
We see your actual screen, your desktop, not if you're presenting somewhere, we're not seeing that.
Uh-oh. Do you see my cursor?
We see your emails and your cursor.
You see my emails and my cursor. Wow.
Share the display, not the window, I think.
It's your note.
Yeah, we're looking at a OneNote.
Okay, hold on. Let me try to do that a little better. Share screen. Desktop 3.
Yeah. Yep.
How's that?
Yeah.
Is that better?
Perfect.
You could tell when things are live. I love it. Okay, so now the final event for IEEE's VGTC's highest VR technical award, the 2021 Virtual Reality Career Award goes to Mary C. Whitten. Before you start clapping, let me just say 2 sentences about Mary. She has had a distinguished career, both in industry and academia. She has co-founded 2 very successful pioneering graphics companies, of which I still talk about regularly. And she has advised generations of students and researchers and colleagues at the University of North Carolina and far beyond. In recognition of her lifetime contributions to the technologies, techniques, and theory that enable virtual and mixed reality systems and its applications to better achieve their intended goals, the IEEE Visualization and Graphics Technical Committee is pleased to confer its 2021 Virtual and Augmented Reality Career Award to Mary C. Whitten. Congratulations, Mary.
Thank you, Henry. I think they're going to put me in speaker view. I'm going to speak without slides. And first, I want to thank Henry and the Technical Awards Committee. I'm honored and humbled to be recognized with this award from my professional friends and colleagues. it also was a surprise. Henry said, "Are you sitting down?" And I said, "Yes, I am." And then he sprung the news on me. I've been fortunate to have a career that's been full of interesting technical problems and the opportunity to work on those problems along many smart, creative, and honorable people, and to work with them in collegial environments in which we could all grow as people and researchers. My career has been richly rewarding intellectually and personally, and an enormous amount of fun. Some people get lucky and get to work places that are just magic. You have a leader with a vision that is shared with the team. The work is challenging, the environment is collegial and supportive. You're recognized for the contributions you make, and your colleagues are productive individually and even more productive as a team. Few get to work at such magic places even once in a career. I've had the absolute good fortune to work in 3 of such places. The first magic place I was in was at NC State University in Professor John Stodhammer's Computer Graphics Laboratory. In the early 70s, John received one of the very first NSF awards for computer graphics research. He had a vision that at that time was shared by only a few. John was a really savvy judge of technical talent, and he hired for smarts and potential that he saw, not on academic record. You can ask some of the members of the team about their undergraduate academic records if you have a chance sometime. Most of his bets on people paid off really well. One of the lessons I learned there was to hire well. John was a smart leader. Not only did he hire well, he shared his vision and got buy-in from the team, and then he got out of the way of his people and let them work and grow. And that's, Dave just said, get out of the way and let the smart people work. Stodhammer's lab group ate lunch together almost every day. My future husband was part of the group, and I hung out with them as much as I could, particularly once I started work on my electrical engineering degree. We used to joke that I was the resident graphics groupie. A lot of groundbreaking computer graphics got talked about over those lunches, and I learned a lot just by sitting there and listening. But perhaps the most important learned by example from the lesson learned by example around that table was that a free and open sharing of problems and solutions and sharing of insights and ideas increased everyone's productivity and moved the research further and faster. John's lab was my first experience with a magic work environment. The second place I worked that was magic was actually 2 places. My husband, Nick England, and I founded 2 companies, Iconis Graphic Systems and Transept Systems. This was a huge shift for us, for we were now looked to as the visionaries and the leaders, not only of product and engineering effort, but also in creating the work culture. But we'd seen it done and done well in John's lab. There were many things we didn't know how to do, but we knew we had to hire well. Among the very small Iconis engineering team, we fostered respect for what each of us knew and contributed. After all, it was the most time and cost effective for us to defer to the most knowledgeable person. Defer that was until we thought their ideas needed to be challenged. Transept, after acquisition by Sun, grew to over 60 employees in North Carolina. We made very good hires in our engineering managers. They were both leaders in technology development and in continuing and deepening the collaborative and supportive culture we had established. I think it's one of the most satisfying things in my life that former Sun North Carolina employees still say it was the best place I ever worked. That particular magic ended when Sun closed the North Carolina engineering office. So what next? My third magic job has been being a part of the graphics group at Chapel Hill. Shortly after Sun shut us down in 1993, Dr. Fuchs called me and asked if I'd like to talk with him and Dr. Brooks about managing the UNC graphics lab. Well, yeah, I was pretty sure I'd like to do that. And it's a very good thing Henry couldn't see the happy dance I was doing when he called that time. Working at UNC has turned out really well for me, and I hope Henry and Fred think they hired well. At UNC, I've had more good problems and technical challenges to work on, more good people to work with, and that all important collegial environment, the magic. I've had a wonderful career, and I owe thank yous to many who are part of making it so. As David also said, you don't do this by yourselves, and most of the work is done by the folks you work with. My primary collaborator is Fred Brooks, and it's been my great privilege to work with him and our Effective Virtual Environments research team for more than 20 years. And it's really lovely to see so many of you on the call. Thank you guys for coming. Thank you, Fred, and thanks to our 20+ students who are now our colleagues who have gone on to do wonderful things. But besides working with Fred, I led and worked on teams with 7 other faculty members in computer science and other departments across the UNC campus, and in 6 collaborations elsewhere in the US and around the world. Each project involved an interesting and worthwhile problem and those same smart, creative, honorable, and fun people. Thank you to all these collaborators and their students. I started trying to count my co-authors and just gave up. It was too hard. But there are a lot of people who did the work that led to this recognition from me. My thanks are not complete without expressing my really deep gratitude to my husband, Nick England, for his constant support over these many years. Nick, I couldn't have done it without you, and we couldn't have done it without each other. I have one concluding reflection. I learned from both Dr. Staudhammer and Dr. Brooks the value on focusing on growing people at the same time as you're doing high quality research. I like to think that, following in their footsteps, I have done that too. Thank you.
Thank you, Mary. And thank you, David. This concludes the 2021 award ceremony. I want to add just a final personal note. Despite the fact that I have had the privilege of knowing and working with both the award winners, I had nothing to do with this. I did not nominate them. I did not vote. I did not count the votes. I had nothing to do. When the votes were announced by the 2 tabulators, it was a complete surprise and delight to me, as it was, I'm sure, to the rest of the awards committee. Thank you, one and all. Goodbye for now.
Thank you.
And thank you, everybody, for joining us in this welcome reception. And I guess from what Rob Lindemann tells me, everybody's kind of thrilled and excited to get on this treasure hunt. So I won't deter you from it. It was really an unexpected pleasure to meet so many old friends and colleagues. And I would like to join my congratulations to Mary Whitten and David Luke, 2 people who I admired and respected over the years, and I have the privilege to call friends. Deserve congratulations, and I could not imagine a better way to send off IEEE VR 2021 than this. It was fantastic, and I hope that everybody can continue to enjoy IEEE VR 2021 in these difficult times. Thank you all for coming and for sharing. See you around.
Thank you. Goodbye.
Thank
you. See so many of you.
Goodbye.
Are we taking
See
a
you
photo?
all soon in VR.